Ladies and gentlemen, let me welcome you to the 16th EAI International Conference on Heterogeneous Networking for Quality, Reliability, Security and Robustness, EAI QSHINE 2020. I am Aleksandra Stadziejowska, and on behalf of the EAI, I would like to use this opportunity to address the organizing committee, the authors, and our online audience. First of all, I would like to thank all of you for being a part of this conference and for your involvement with the European Alliance for Innovation. Above all, I would like to express my gratitude to the General Chair, Xi Wu, and the Program Chair, Kong Wang, for their excellent work in the organizing a successful conference in these difficult times. Also, I am very glad to be able to announce that the 17th edition of EAI QSHINE will take place in Australia. I invite all of you to participate in our 2021 edition by submitting your papers, by organizing a workshop, or by joining the Technical Program Committee. In fact, at EAI, we are constantly searching to promote innovative research in the field of information and communication technologies. So if you have an idea for a conference or a workshop, or you want to collaborate with us in any other way, please contact us at the email address below. Each presentation will be streamed in this channel with a parallel ongoing discussion in Slack. I invite all of you to take part in this live Q&A session in Slack by following the link below this video. In a few moments, my colleague Michal will tell you more about the EAI entity and tools we provide. Thank you all for the attention and enjoy the conference.
Hi everyone, my name is Michal Dudic. I'm the Community Manager at EAI, European Alliance for Innovation. It's my pleasure to welcome you at this conference and say a few words about who we are and what we can do for you and your research career. In short, EAI is a global community for a greener, healthier and smarter world. As of today, we are home to more than 60,000 members from 167 countries, and we reach out to tens of thousands of subscribers. As an organization, we are non-profit from day one, and what is most important to us is that we remain open to all researchers from all around the world thanks to membership that is completely free. We organize more than 100 events annually, such as this conference, and we do so in publishing partnership with Springer. I said in the beginning that EAI is a community, so let's talk about what that means and what it means for you. To put it briefly, we give our members a platform that builds their research. We do it with 3 main online community services where members come together to help each other write a better paper, get an objective review, and get recognized fairly. The 3 services in question are EAI Compass, Community Review, and EAI Index. Firstly, EAI Compass is an online app where you can meet and connect with new colleagues and get feedback on your paper as well as your presentation. In addition to that, it lets you download all full papers that will be presented at this conference, and you can vote on your favorite presentations as well as see everyone who is here and connect with them. You can do this right now if you go to EAI Compass website, compass.eai.eu. Next, we are improving the classic conference review process with community review. It has already been in use at all our events since 2019, and we were very excited to hear a lot of positive feedback from program committee members regarding the reliability and the speed of the community review. Let's talk briefly about what community review does. Essentially, it is a website that shows abstracts of papers that are right in the middle of the review process, as long as the authors allow it, of course. And all EAI members may then bid to review specific papers. When they submit their bid, they put in their bio and their qualifications, which are sent to the program committee, who can then decide whether or not this bidder is qualified to review the paper they bid on. This relatively easy access to review opportunities means that bidders really need to put their best foot forward if they wish to be selected, which improves the quality of the entire review process. At the end of the day, this benefits you, the author. And last but not least, let me tell you a thing or two about EAI Index. EAI Index is our credit-based evaluation system that we rolled out this year to all of our conferences and journals that allow you to climb the global ranks of EAI community and get recognized for your work. It calculates a number value for most actions you make, such as getting your paper accepted or submitting a review, and these numbers accumulate for 12 months. At the end of this 12-month period, we put together a ladder of all EAI members, and the ones at the top receive a nomination to one of the membership ranks: senior member, distinguished member, or fellow. For each action that is eligible for EAI Index credits, we'll look at the quality of your action as it was evaluated by another member of the community, such as, for example, the review score of your submission. To make sure that the system is fair to newcomers, every 12 months the credit count gets erased, the ones at the top receive their nominations, and every member starts at 0 for the following 12 months. And finally, Smart Submit is a collaboration feature that is coming later this year. It will allow you to submit your research ideas and your work in progress abstracts to get the kind of help and feedback you're looking for. Maybe you are looking for co-authors, maybe you would like to find a mentor or a mentee, or maybe you want to find out how the community feels about your idea. This is what Smart Submit is designed for. Ultimately, it's about helping you write a better paper and increasing your chances of getting accepted. Again, we will be launching this feature later this year, so stay tuned. And so I'm going to leave you with many different ways to get engaged at different levels. There are lots of opportunities in many of our events and publications, which means many ways to connect with people and collaborate. You may learn more about everything I just talked about at our website, eai.eu. These services exist to help you and to make your lives easier, so we encourage you to send us your comments, ideas, and feedback to community@eai.eu. And if you're interested in volunteering and contributing, you can let us know at the same email address. Don't forget that you can use EAI Compass to vote on presentations in real time to determine which ones are the best, as well as to download all full papers that will be presented today. Just make sure that you log in using the same email address as the one you used to register to this conference. Thank you very much for your attention. Please enjoy the conference, and I hope we will see everyone online soon.
Hi everybody, I'd like to talk about estimating socioeconomic status using big data. Here in the case of smart card data. So my name is Xiaoming from University of Göttingen, Germany. So firstly, the talk is organized as follows. So what is a socioeconomic status? SES is typically used as a shorthand expression for variables which characterize the place for persons, families, or other aggregates with respect to the capacity to create or consume goods that are valued in our society. This is according to Hauser and Warren's paper in 1972. So effectively, SES is to characterize one's social and economic position in relation with the others. So this is one of the most important notions in social science. And typically, it's estimated by education, income, and occupation, 3 dimensions. These typically also using by sociology surveys. And for example, census, which takes every another 10 years, or using household sampling, which is only 1 or 2 or 5% of population, which is rather small size. And of course, estimating SES has its economic value. So it might be useful for estimating the poverty, for example, and the social policies, and it can be also useful for help the government to decide and the business to decide certain customized services. For example, digital marketing or bank loans. So the introduction or the emergence of big data could have a lot of implications to understand the society. So if effectively a person footprints in a digitalized society can leave a lot of new data like digital life, digital trace, or digital life. So digitalized life. So digital life here means that people are using internet platforms to do some data analytics. So, for example, people can utilize a Twitter footprint to estimate one person's SES. And secondly, one can use digital traces, for example, using the historic events where they have happened. And this could be using a location-based system or CDR data from the mobile phones to estimate the SES. And thirdly is digitalized life, so which can be reflected by non-digital life, captured by the digital form. So this is how, for example, the cities or Google Books or some other things that recorded by some behavior pattern by sensors or some other type of consumption or behavior data recorded by non-digital life. Okay, so here, the temporal spatial composition of digital footprint can be used for estimating SES in general. And instead of using sociological surveys, big data offers a big opportunity for estimating SES, thus serving for a future development for socioeconomic solutions to improve the human beings. So the let's say assume we have SES, 3 levels of SES, high, middle, and low. Can we estimate those 3 levels by human mobility data? So here, mobility itself, it can have implication to the SES. And in our context, many trajectory data recorded by a variety of means, such as smart card data, which is recording the digitalized life of a person. So we can see how SCD or smart card data could be useful to estimate SES. So let's say why this SCD trajectory could be useful to estimate SES. So here illustrates an example where you can see here, for example, when a doctor, medical doctor, is daily pattern like this. Let's say you can see here, there's an office building, there's a shopping mall, there's a government, the bank, and the medical center, and the residential area, and so on. Very complicated trajectory. And if it is a TV director, so it will go for some places like tourist attractions or the cultural centers or shopping centers as usual. But you can see here, they have a lot of time to go outside and in particular cultural centers. And thirdly, if it is an IT programmer, you will see that the trajectory is quite straightforward. majority mobility pattern takes place between office buildings and residential area. So you can occasionally go to the tourist attractions or villages or middle school or government. So this suggests that the trajectory of a person should be very likely having some relationship with a person's SES. As we say, SES estimation using mobile phone data could be one possibility to understand the cyberspace features like daily contact, callers, social network, to do the SES to see how much social or economic position in the society could be. And you could also utilize social media data, for example, predict the personal income using tweets, or predict the occupation using tweets, and so on. And thirdly, one can aggregate some user groups from user patterns. So if there are some user groups could be higher than the housing price they buy the immobilian marketplace, they will buy some how high or low different kind of user groups could reflect their different purchasing power, and so on. So the existing work, all these aspects would have never covered the problem of individual mobility pattern will be useful to estimate the individual SES. So this is the question for today, that we understand this problem from a Shanghai subways data set, which is unlabeled, and we have to do a lot of data pre-processing. So after the data pre-processing, there are close to 8 million user IDs, and there's no anything about the personal data, and it only records the temporal and spatial information, which is about the time and the station name if a user takes the subway. So within the 16 days, we have more than 60 transitions and 290 subway stations. We also crawl the POI, point of interest of Shanghai, leading to 12 categories and more than 500,000 points, POIs, so which can be denoted as different type of locations, business residence, hospital, hotel, and so on. So the third data we are integrating here is housing price about Shanghai. So this is crawled from famous immobilian market website, lianjia.com, which depicted many different regions in Shanghai about their housing prices, ranging from the different, let's say, between 10,000 yuan per square meter to close to 100 yuan per square meter at the time of 2016. So ground truth data here is we have to see how we can denote them as useful input to do the labeling. In this label is based on our third-party data instead of the SDD data. So we have there are many users. Only, let's say, only 22%, 22.8% are frequent users with subway. Takes a subway for more than 7 days out of these 16 days. So we then think about how we could utilize this. And secondly is the SCD IDs are not the original SCD IDs which are associated with the real card. So the data set we got is actually cannot be useful to doing some social experiments by, for example, getting some cross-sourcing data by asking their users SCD ID and with some bonus about whether they are associated with their other socioeconomic properties. For example, telling their basic occupation or education level and so on. All this data is not possible. Income is difficult to infer through the SACD IDs. So then the question of how to approximate SES here is become very tricky. So here we utilize a housing price or area level income to do this. And unfortunately, if we use county level income, it's too curve-framed. So each county is about 20 stations and nearly 1 million people are living there. So this is not useful at all. So then the housing price and income level, this correlation from our preliminary study is quite relevant. Therefore, we assume the housing price level is quite a rough estimate to approximate SES. So then we label from the home station of each user with label the user with housing price range, and then we can get a notion about each individual's rough SES level. Okay, so how we can do this? So we have now we say we have three types of input: POI from the map, and the raw SCD, and also housing price. These three type of things. For the first two type of data sets, we can derive the general feature and sequential features. And for housing price, we can infer the user's SES label, and then we fit to the deep learning model to understand what is the potential accuracy of a prediction SES. So now we have the general feature, general statistical feature, which contains about the how much data user is moving in, how big is a moving area, and how much stations they have regularly commute, and also how many times they are visiting different stations, and the activity diversity in terms of spatial diversity. This also can be characterized with such features, and also from the different origin stations and destination diversion stations, those travel diversity can be also a general feature for a user. Secondly, there could be a lot of sequential feature in a day. Let's say each of the 16 days will be divided into time bins for every 15 minutes with a time bin. And for each time bin, we can find the staying station and calculate the feature vector of the staying station. So then this feature vector of the station at any time bins, then we will have three types of features. One is the ID, one is the function about the station, and then the function of function for the current user. So these characterize the sequential feature for each of the station and each of the user. So this is effectively using these two types of features, sequential and general feature, and then especially for the sequential feature, we can utilize the multi-layer LSTM model to do the final estimation, and also using a general feature, we can then combine together and derive generalized softmax effectively eventually determines whether its SES is more close to middle, high, or low. Okay, so sequential components would characterize the lifestyle, and those detailed calculation is actually depicted by the feature and the embedded nature and transformed into some formulas, and finally get to the estimation about the most visited, let's say, most likely intended nature. And for the general feature, we also have the this general feature is also commonly known in the mobility pattern learning. So this will utilize this information from the sequential feature and general feature together and combine them and assign the weight, and finally got the softmax function and estimate the final SES level. So with this fusion of sequential and general feature integration, and using the training for such a phase, and then we can make the optimum setting and train the deep learning model effectively to derive a good parameter for the next time prediction. So here we do extensive evaluation using the a partial set of the users to do the verification about our developed model. So these more than 720 users are used for this performance evaluation. So this characterize the users of frequent travels using subways. At least there are 7 days of subway use out of these 16 days. And also those users can recognize their home stations. So we utilize the middle, low, and high SES based on their housing price ranges. So each with different percentage in the distribution. So we pick 80% for the users for learning and take 20% for testing. So we also utilize 3 types of accuracy measures: precision, recall, and F1 score. So the comparable other solutions are: one, random guess, and secondly, STL model, and thirdly is gradient boosting decision tree. And also there's a light GBM model, which utilize the GBDT model. So we have done different variables about our proposed solution. For example, we take sequential model only, or take general model only, or we combine sequential and general models together. So here the table plots our evaluation result. So our you can see from this table, for this 3-class classification problem, we are able to achieve the accuracy in all the three measures of the combined solution using sequential and the general feature as the highest accuracy. And second to this is the SES, the S, only the sequential model would already take the highest accuracy, second to the sequential plus general features. So then the light GBM would underperform our S2SS and SG models, which demonstrate our beauty or the benefit of introducing sequential and general features in the deep learning model, which performs very well. So, of course, there are some possible consequence of our estimation. So many users in the high SES levels are estimated as middle SES. This is one problem here. And also the difference between the SES difference levels are not very clear. So remember, subway tickets are typically used by low and middle income level groups. So the SES level, even if they are having such a so-called high income or high housing price level, they are not necessarily really rich. So therefore, we have to make a careful assertion here. The third is the mobility difference might be not very clear. So the middle and high level housing price nearby stations are clearly nearly to each other. Therefore, it's the difference between the mobility pattern might be not distinguished enough. So we need to think about those mobility pattern, sequential pattern, and also the general features carefully, and better to perform additional surveys to understand whether the location and their income levels are accurate enough. So to conclude this, we have presented our first attempt to understand SES from a spatial temporal mobility pattern alone without the real income and the real education levels and so on. So with such SCD level, SCD-based mobility data, we are able to infer the SES level with a certain accuracy. So of course, the ground truth accuracy itself requires further study, and some further important temporal spatial features are necessary to be incorporated. So we wanted to know more details about the reasonable scale between the SES and mobility. And also, if we can know the mobility data is incorporated with the semantic data, like where I am and like users check-in data, would be very useful. So probably some other type of user data, like the online social network or LBS data concerning text plus location plus temporal, those features can be jointly determine a person's ES better than the SCD data alone. Thank you very much for your attention. Any questions and comments are welcome.
Hello everyone, I'm Liang Boxi from Chongqing University of Posts and Telecommunications, Chongqing, China. So I'm glad to be here to share our research. The title of our research is Energy Efficient DAC Scheme based on Unit Capacitor Switching for ADCs. So, wearable devices are very popular in our daily life now, so they can monitor our health conditions like the heart, breath, and breath conditions. So all these health conditions are monitored by the sensors, and if we want implanted these sensors in our body, so we want them to work very long. That means we need these sensors to be very low, to be with no power. So as the key part of the sensor, the analog to digital converters are very important in the sensor. They can convert the analog signals to the digital signals that will display on our screen or displays. So how to choose the ADCs? There are main 4 types of ADCs. The first type is flash ADC. It has high speed, no resolution, but the power is very high. If the resolution increases, the competitors in this ADC will increase significantly. That will make the design more power hungry. The second type is a pipeline ADC. It has high speed and it's also power hungry, and has medium resolution. The third type is the SAR ADC. It features low power, medium resolution, and medium speed. And the fourth type is the Delta Sigma ADCs. It has very high resolution, but its speed is very slow, and it's also power hungry. And there are some other ADCs, some hybrid architecture, okay, so such as time-interleaved SAR ADC, okay, it's usually used to increase the speed of the ADC. But the design complexity is very high. So in our wearable device, the signal is usually in kilohertz. So the SAR ADC is a very good candidate for these applications. And in this paper, we will focus on the SAR ADC that is suitable for low power applications. So this is the structure of a SAR ADC. It has competitor SAR control logic and capacitive DAC. Okay, here DAC is the digital to analog converter. Okay, so in the SAR ADC, the CDAC dominates the overall power consumption of SAR ADC when the sampling rate is tens of kilohertz. That is this signal with such kind of frequency is usually of our interest. Okay, so because the heartbreak is usually below this frequency. Okay, so as we just mentioned, so the CDAC usually dominates the overall power of the SAR ADC. So how to improve the DAC power efficiency? So we first focus on the energy consumption of the CDAC. Okay, this is energy we can derive from this equation. So it can be seen here. The energy consumed by the capacitor is corresponding to the value of the capacitor, and the voltage reference, and the voltage change between previous state and the current state. Okay, so from this equation, we can see that the ways of improve the energy efficiency. So the first one is decrease the energy consumption of the first MSBs. So here the MSB means the most significant bit. So why is this very important? Because MSB is usually occupies a very large part of the CDAC, so the power consumption is also very important. And the second is to decrease the total capacitance. Okay, this is very clear from this equation. So when the capacitance is very large, so the energy consumption is also very high. And the third is the reference voltage. So we can reduce the voltage reference, but it seems a little hard because the voltage reference is corresponding to the signal, okay, the swing of the input signal, and it determines the input signal range, right? Okay. So based on these observations, so we proposed the structure of this ADC. So the architecture here contains the capacitor here and the side control logic and the CDAC. Okay, so it has three voltage reference. The first is Vref, and the second is VQ, and the third is GND. This means the ground. Here the VQ in this design is equal to 1/4 of this voltage reference. Okay, and please keep in mind here. So pay attention to here. So the CDAC adopted in this design is capacitor splitting architecture. So this means the MSB capacitor is split into capacitors the same as the rest of the capacitors. Okay, so here we call this the MSB subarrays, and the rest is the LSB subarrays. So both these arrays are with the same architecture. Okay, the same configuration. So we will explain our DAC switching scheme using a 5-bit model. Okay. During the sampling period, so the input signal is sampled on the top plate of the capacitor. So this is called the top plate sampling technique. Okay, so when using the top plate sampling technique, so the MSB will be obtained by directly compare the voltage sampled on the P-side capacitor and the N-side capacitors. Okay, so this stage there is no power consumption. So, and in this example, so we only show the VIP larger than the VIN case. Okay, because the comparison is symmetric, so we only show VIP larger than VIN here. Okay, that means here B4 is 1, the bit 4 is 1. After the B4 is obtained, we can collect the LSB subarrays from 1 to 1/4 here. Okay, we can see here the 1 means the Vref and 1/4 means VQ. Okay, so we can change the voltage collections from 1 to 1/4, and the MSB capacitor of the negative side. Okay, from 0 to 1/4. With these changes, okay, the voltage change is 0.5 Vref, right? So we can do this. After this, we can compare the voltage of the positive side and the negative side. If the compare result is 1, then we can change the capacitors of in the LSB array of the positive side from 1/4 to 0. and simultaneously we also change the capacitor in the MSB subarrays of the negative side from 1/4 to 1. Okay. In this way, we can achieve a 1/4 voltage VREF change. And if the B3, the compared result of this step is 0, so we can change the MSB subarray of the positive side from 0 to 1/4 and change the capacitor in the negative side, okay, of the ASB subarrays, okay, from 1 to 1/4. This step also achieves the 1/4 voltage change. Okay. So from this step, if we have a n-bit SRDC, then from the MSB 2 to the ARSB 3, we use this width to do the SAR process. And for the last 2 bits, we can use these steps, okay, to get the last 2 bits. And this will be shown in the table, which will be explained later. Okay, this is our proposed dummy capacitor switching method here. Okay. So here we called these 2 capacitors unit capacitors, and these 2 groups are dummy capacitors. Okay, this is capacitor operations of the last 2 bits. Okay, so it seems this control logic is a little complicated. Okay, so this is a simulation result, and this is simulated in the MATLAB using a 10-bit model. So from this figure, it can be seen that the switching energy of our proposed switching scheme is the lowest. Okay, and this is a comparison with other existing techniques. Okay, it can be seen that the switching energy and the area of the deck area is the lowest. So this is a simulation result of the DNL and NL. So the DNL means differential nonlinearity, and NL means integral nonlinearity. So the maximum DNL is 0.259 ARSB, and the max NL is 0.242 ARSB. Okay, that's all for our research. Thanks for your attention.
Ladies and gentlemen, it is an honor to present the paper entitled The SDN-governed ad hoc swarm for mobile surveillance of meteorological facilities. On behalf of all the authors, my name is Shi Chen, I'm from the Southwest Minzu University, Chengdu, China. First, let me introduce the paper. Meteorological facilities require close and mobile surveillance to work properly, especially for those facilities deployed in fields, in remote areas, etc. But these facilities are hardly within the reach of convenient surveillance and reliable network infrastructure. So there exist some challenges. Some of the facilities are out of the range of fixed cameras or obscured by unexpected objects such as growing trees, falling rocks, etc. We can see that problem at Q1 here, Q1 in this figure. Okay. These facilities might also be damaged by wild animals. Q2 we can see here as a squirrel is damaging the temperature sensor. All right. Or severe environmental conditions such as strong wind. Okay. So the ad hoc networking is a candidate for mobile surveillance of meteorological facilities deployed in fields. However, some issues must be also addressed. The first challenge is the consistent control over the whole swarm, mobile swarm, because it's a peer-to-peer distributed structure. Okay. The collaborative on-site formation adaptation, to avoid some rocks, to get better monitoring angles, etc. Okay. It also requires some image recognition capabilities to let the administrator know as soon as possible what kind of damages are being made. Okay. So one solution to deal with all the challenges is to apply the centralized SDN on top of the distributed ad hoc underlay. SDN is short for software-defined networking, which is extensively studied in academia in recent years. So we propose the SDN-governed ad hoc swarm for mobile surveillance of meteorological facilities. The contribution of this paper includes as follows: a tunneled overlay structure based on VXLAN, which is Virtual Extensible Local Area Network, that bridges the ad hoc protocol stack and the SDN protocol stack to implement uniform control over distributed underlay. The second contribution is the extended open flow to accommodate self-defined physical actions so that mobility and sensibility of the ad hoc swarm can be consistently controlled without evolving hardware details. The third one is it combines with the TensorFlow-based image recognition. And the fourth one is a prototype of low-cost mobile surveillance ad hoc swarm governed by SDN is implemented on Raspberry Pi platform. Okay, first let me introduce the mobile node architecture. The architecture of the ad hoc mobile node is divided into 3 layers. The first layer, the lowest layer, is the hardware layer, which is based on the Raspberry Pi platform. The second layer, the operating system layer, provides software functionalities like networking, computing, storage, etc., perhaps based on Ubuntu, something like that. The SDN layer, which is the key extension for the centralized control over the distributed ad hoc underlay. So every node is equipped with the SDN data plane, the Open switch, OVS for short, okay, and also the SDN control plane, floodlight. You can see from the figure, okay, So we first conduct the ad hoc underlay networking. The wireless network interface card of every mobile node should be configured to work in the ad hoc mode. The script below specifies how to configure the ad hoc mode. We can see that we first specify the IP address, the network mask, the network prefix, the broadcast address, and what is very important is here we specify the SSID of the wireless network card as my swarm. The name of this is SSID. Okay, you can take any kind of name as you wish, but every node in this swarm must be configured to have the same SSID, so they can work together, so they can communicate together. And also we must clearly specify that it works in the ad hoc mode. Okay, that's the configuration script. Okay, so after we have done the ad hoc underlay networking, we conduct the SDN overlay networking. The first step is we construct the tunnel overlay structure. The key to deploying the SDN overlay above the ad hoc underlay to offer consistent and streamlined control is the deployment of OVS, Open vSwitch, the OVS, which is also the most widely used SDN switch, virtual switch. Okay. The actual traffic forwarding is done by data path provided by OVS. Data path. You can imagine data path as a switch, a virtual switch, Data path can be created on demand by OVS and equipped with multiple vPorts, virtual ports on the data path for traffic ingress and egress. Okay. And every wireless network interface card of mobile nodes must be bound to data path created by OVS, so that traffic flows run into OVS modules, leading to an direct control by OpenFlow. So the OVS is the virtual switch deployed in every mobile node, and the OpenFlow is the network protocol that is used by SDN controller to control how the traffic goes from one vPort to another one, directly controlled by the controller. So in every mobile node, we create an OVS data path named BR0. At this point of time, every node has two forwarding devices: the physical wireless NIC WLAN 0 that has already participated in the ad hoc underlay networking as we previously specified, and the virtual data path BR0 that will participate in the SDN overlay controlling. Okay. So in order to achieve this purpose, and in order to encapsulate WLAN 0 without compromising the ad hoc underlay communication, it requires end-to-end tunneling over the physical communication channels by means of data path and vPort. So we use VXLAN for this pairwise tunneling by means of the following script. This following script, it uses this OVS VS control utility. First, it add a virtual port, vPort 1, to the BR0 data path, and set its mode as VXLAN mode, which is a tunneling mode, and clearly specify the remote IP, the IP address of the other end of this tunnel, the outside IP address. Okay, and it also set the controller of this bridge to be the SDN controller deployed on this IP address. And 6653 is the port that is used by the SDN controller. Okay, so the whole ad hoc swarm has one SDN controller and several mobile nodes to be controlled by this controller. Okay, that is the structure. Okay, so here the 10.0.0.0.1 is the IP address of this SDN controller of the swarm. Okay, all right. So after we have accomplished the tunnel overlay structure, we also need to implement decentralized controlling. Okay, the OpenFlow protocol is originally designed to instruct data forwarding on switches, no matter it's a physical switch or a obvious virtual switch, as long as they support SDN. Okay, but to fully control these mobile nodes, since every mobile node involves moving, sensing, monitoring, etc., to fully implement the control and management of mobile node using OpenFlow, the OpenFlow must be extended with corresponding actions that controls not only data forwarding, but also moving, sensing, monitoring, etc. So we can see from the right figure, this part, it exhibits the traditional data forwarding actions provided by the original OpenFlow. These parts, such as moving forward, moving backward, moving left, moving right, they controls the movement of mobile nodes that we extended. Okay. It also controls cameras for camera recording, camera on, camera off, and also offers image recognition capabilities by using OpenFlow, So, as we just mentioned, the whole swarm has one SDN controller. It supports OpenFlow protocol, so this controller can control all the swarm using the extended OpenFlow, because it has already supported moving, sensing, recording, something like that. Okay, that is why we extend the OpenFlow protocol. Okay. So we also developed the image recognition feature deployed on the Raspberry Pi platform based on TensorFlow and OpenCV framework to identify several harmful creatures around the meteorological station. We selected the SSD MobileNet V1 network and the pre-trained SSD MobileNet V1 COCO model to conduct the transfer learning to accelerate the training. MobileNet is a lightweight neural network model proposed by Google in 2017, which is suitable for embedded mobile nodes that we used to network a swarm. Okay, they are short in power, in computing capabilities, something like that. So we use this embedded machine learning framework. Okay, and we also did some evaluation to our ad hoc swarm that is governed by SDN. We implemented the swarm networking and centralized controlling first. Okay, the hardware platform is the Raspberry Pi, and the operating system is Raspbian OVS, which is the native operating system of Raspberry Pi. And we also installed SDN controller, the floodlight on every mobile node, and the SDN switch on OVS on every mobile node, so that every node is able to be selected as the controller, and also if it is not selected as the controller, it is a controlled node by the controller. So the whole structure is a ad hoc structure, peer-to-peer ad hoc structure, as we can see here in this figure, a 3-node swarm. On the lower level, they are peer-to-peer ad hoc swarm. But since we installed the SDN controller that uses OpenFlow to control the data forwarding of every node, the moving, the monitoring, the sensing of every node, so on the top, on the higher layer, the swarm is a centralized controlled swarm. Okay, you can see that from P2 is the controller, and P1 and P3 are controlled nodes. So we can see that in P2 the overlay SDN topology, Okay, we also did some evaluation about the SDN control traffic forwarding. We can see from figure A the flow entry that drops the traffic between P1 and P3. Okay, we push this entry to P1 and P3 from the controller P2, and we can see that the pin traffic has been disabled here. Destination host unreachable. Okay, traffic has been disabled. And if we delete the traffic dropping flow entry as we just installed in Figure A, you can see that traffic has been enabled again. The pinging is successful. Is successful. Okay, so it proves that the whole swarm can be controlled by just one SDN controller. Although it is essentially an ad hoc swarm, but it has been logically controlled by the SDN controller deployed on P2. Okay, and every node can be controlled by the SDN controlled physical actions. We can see here. We send some actions. W, S, A, D. W means forward. S means backward. A means left. D means right. By SDN messages to every node. So the node can move forward, backward, something like that. Okay. One thing you have to notice is that the controlling is totally conducted by the OpenFlow protocol. So it is a very convenient structure that controls not only the data forwarding but also the moving, the sensing, the monitoring, etc. Okay. And we deployed our ad hoc swarm, the SDN-governed ad hoc swarm, to conduct the mobile surveillance and image recognition around a meteorological station in university located in Chengdu. Okay, this one is the meteorological station, and the swarm that take close surveillance takes close surveillance of all the facilities like a radar, something like that. These are the images. These are the pictures taken collaboratively taken by these nodes. Okay. You can also see that some harmful creatures such as sparrow, squirrel, something like that, can be recognized with very high percentage. Okay. Okay. Conclusions. The ad hoc networking provides good availability and flexibility in non-static network topologies, thus a good choice for on-demand mobile surveillance for meteorological facilities deployed in fields. However, the distributed structure prevents it from being consistently controlled, hence the difficulty in coordination in mobile surveillance. This paper, we propose to integrate SDN methodologies into ad hoc networking to construct a collaborative and controlled swarm, so that moving, sensing, image recognition, etc. are uniformly controlled by the centralized SDN controller by means of extended OpenFlow. This overlaid and hybrid structure simplifies the global control over the SDN over an ad hoc swarm, in that only the SDN swarm head that activates the SDN controller is involved for the manipulation of the whole swarm. Extensive experiments in real-world meteorological station demonstrate the feasibility. In our future work, topology dynamics such as swarm fusion and fission due to the distance variability will be studied to offer finer-grained control over the distributed underlay. That's all for the presentation. Thank you very much.
Ladies and gentlemen, my name is Huan Zhang. I come from Sichuan University. I will introduce a paper, Hardware Trojan Detection Method, based on multi-featured GEP. I will introduce the paper in 6 parts. Introduction. In today's hardware, Trojan detection technology, destructive reverse engineering can most precisely restore the original circuit of the chip to be detected. But this technology is a huge amount of work, high cost, long life cycle, and the chip has been scrapped after detection, can only be used for sampling or replication of a class of chips. Bypass detection technology analyzes the bypass circuit signal, such as timing, power, electromagnetics, heat, etc. Determine whether or not they contain Trojans. No damage to the chip. Relatively small amount of data is needed. Lower cost is the most important and effective method. Some of the work is done by evolutionary algorithms to study evolutionary hardware. This paper proposes a multi-featured GEP evolutionary algorithm. Use a single circuit component or group of circuit structures as a node. Use an operator to describe a node's multi-features. Use GEP to evolve circuits close to the original circuit. Then determine the structure of the original circuit. Brief introduction of GEP. Gene expression programming combines the advantages of GA and GP, following the basic steps of evolutionary computation. The basic composition of its genetic material is 2 kinds of symbols, that is, determinators and functions. A gene consists of a linear, fixed-length string of symbols, code for expression trees with different sizes and shapes. A chromosome can consist of a single gene or multiple genes. Each chromosome is decoded to map as a candidate solution for problem response. For example, a GEP chromosome in graph A shows the expression tree in graph B. Then it can be decoded into expression in graph C. The bold string in the chromosome is a valued gene in graph A, and the other characters will be lost in decoding. Use GEP to represent circuit. As can be seen from the data structure of GEP, GEP can solve tree structure problems very well. In other words, circuits that can be represented as a tree-shaped structure with n leaf nodes can be described directly with GEP. But if only logical values are used to represent the circuit, There are two main isomorphic situations. For example, in the circuit in Figure 1 can be replaced with the circuit in Figure 2. And in the second circuit, input B is not used at all. That is, input B in the first circuit does not actually affect the output. Thus, only a logic value is used to learn a certain kind of bypass information to describe the circuit. So much isomorphism that the circuit structure could not be confirmed. In this paper, a multi-featured GEP algorithm is proposed. Use the same structure in GEP to represent multiple circuit features. Effectively reduces the number of isomorphic circuits, and use this algorithm to detect hardware Trojans. Multi-featured GEP. In this paper, the logic value of the circuit or any kind of bypass information, such as voltage, current, etc., is called a featured value. Isomorphism for a feature value. Essentially, the features of the circuit components on this feature value are superimposed on each other. Allows several different circuit structures to exhibit similar or even identical features after the feature value are superimposed on each other. This makes it impossible to represent the corresponding circuit by the result of a particular feature value. While we are doing the test, multiple feature values are detected at the same time. The detection results of each feature value can result in multiple isomorphic circuits. But since the overlay features of different feature values cannot be identical, these homogeneous circuits cannot be exactly the same, and the same part of which is a possible real circuit. The multi-featured GEP algorithm can be illustrated by a NOT gate designed by a triad. We can describe this circuit in three different featured values. The circuit cannot be determined if use only one of the features. However, if the three cases are combined, the circuit structure can be determined. Then we include these multiple detection values in a function. The input of the function is multiple feature values. The output is a vector. Like this no-gate circuit in GEP's expression tree, it is still represented by NOT, but the implication becomes the calculation of the vector. For example, corresponding to this no-gate circuit, the symbol NOT indicates this meaning, where A represents the logical value 0 or 1, represented by the voltage entered at point A. The VA represents the input voltage of point A, and the CA represents the input current of point A. Thus, when using GEP evaluation, a single symbol NOT can also represent multiple feature value tests that are not associated with each other. The fifth part is experiments. Figure 4 is a circuit that has no Trojan, and Figure 5 is a circuit that has a Trojan. In the following experiment, the input value 0, 1, 1, 1 in binary will not be provided, and the output of this input value will be determined by the evolved circuit. 4 groups of experiments are designed by using the same parameters. In the first group experiments, none of the 100 times experiments can discover the Trojan circuit if only the logic values were provided. In the second group experiments, also none of the 100 times experiments can discover the Trojan circuit if both the logic values and the voltage values were provided. In the third group experiments, the Trojan circuit was discovered 72 times among the 100 times exercise when the logic values and the voltage values were provided. In the fourth group experiment, the Trojan circuit was discovered 67 times among the 100 times exercise when 3 feature values were all provided. In this group of experiments, 3 feature values were used, but the efficiency of discovering the Trojan was similar to experiment 3, which used only 2 feature values. The reason is since the logic value itself is expressed in terms of voltage values, then the 3 feature values are equal to the 2 feature values. Conclusions. This paper has proposed a multi-featured GEP algorithm. When multiple feature values were fused into the same operator, there is a certain probability that GEP can automatically discover the evolutionary power of mathematical formulas to discover Trojan circuits. The fewer features used, the more efficient GEP evolves. But further away, the conclusion is from the real circuit. On the otherwise, the more features used, the less efficient GEP evolves. But the conclusion is closer to the real circuit. However, if there is a direct conversation relationship between the multiple feature values used, the feature values can be considered 1, and this situation does not increase the evolutionary accuracy of GEP.
Hello everyone, I'm honored to have the opportunity to present the work of our team at the conference. Our study is based on the embedded GPU. So, this presentation topic is Research and Application of Visual SLAM based on the embedded GPU. Here is my presentation content. I divided the content into the following 4 parts. What is the meaning of the SLAM? No, obviously not. SLAM here is abbreviated from Simultaneous Localization and Mapping, also known as Concurrent Mapping and Localization. In order to achieve fully autonomous work in the unknown environment, mobile robots must solve 2 basic problems of positioning themselves and perception of the environment. Simultaneous localization and mapping was first proposed by R. Smith and applied in the field of robotics. It combines the robot's self-positioning and the map construction into one. The purpose of this theory is to make the robot locate itself through the movement of the robot without the prior information of the environment, and then establish a real-time map of the environment based on the sensor data. At the same time, the robot's motion trajectory is accurately estimated. At present, SLAM has relative mature applications. For example, sweeping robot, unmanned aerial vehicle, augmented reality, and visual reality. Moreover, SLAM is also used in the field of autonomous driving and 3D reconstruction. According to the different sensors used, SLAM can be divided into 2 categories, laser SLAM and visual SLAM. Laser SLAM uses LiDAR as the sensor. Visual SLAM can use a variety of cameras, monocular camera, stereo camera, and depth camera as sensors. These cameras are cheaper than LiDAR and are widely used in various fields of society. At the same time, rich color information, texture information, and more recognizable image feature can be obtained from the images captured by the camera. Therefore, visual SLAM has gradually become the main research direction for solving SLAM problems. And the visual sensor's disadvantage is that real-time processing of a large amount of image data requires high computing resources, which brings real-time operation on embedded platforms a great challenge. Compared with the computing resources of high-power consumption PC platforms, embedded platforms generally have low power consumption, and the computing resources are also greatly restricted. Therefore, it is an important direction of the research to use limited computing resources to efficiently execute algorithms of visual SLAM on embedded platforms. For the past few years, GPU computing performance has achieved rapid growth. Its computing performance, especially parallel computing performance, is far stronger than that of CPU. In order to provide a more friendly interface for researchers and developers to use GPU to solve problems, in 2006, NVIDIA Corporation released CUDA, a general-purpose parallel computing platform and a programming model, as an engine to drive GPU to solve complex computing problems, which is more efficient than CPU. At present, there are many algorithms for Visual SLAM. However, most of these algorithms are performed on desktop-level platforms, and there is very little work to solve Visual SLAM problems for embedded platforms. With the development of embedded hardware, high-performance embedded hardware with integrated GPU has emerged. In summary, our work mainly studied how to use GPU parallel computing to accelerate processing on embedded hardware to overcome the computational complexity of Visual SLAM. Visual SLAM system includes 5 parts: visual sensor data, front-end, back-end mapping, and loop closure detection. Our work focuses on the front end. The front end is also known as visual odometry. When the sensor module transmits the image frame sequence to the visual odometry, its function is to extract the key information of adjacent image frames to roughly estimate the camera movement. At present, there are 2 main methods of visual odometry: feature points method and the direct method. In this paper, we use the feature point method. The front end based on the feature point method is a classic method of visual odometry. Feature point method uses the redundancy of the images to detect and extract feature points from the input images, and then performs feature matching and to estimate the camera motion trajectory. And the feature point method runs stably and is not sensitive to lighting and dynamic objects, so it is widely used in the Visual SLAM. For the visual odometry of the feature point method, one of the keys is to use feature detection algorithms to extract the best features from a frame of images. In this paper, we use ORB algorithm. ORB algorithm was proposed by Ethan Rubley and others in 2011. It combines an improved fast corner detection algorithm and a direction normalized brief feature descriptor algorithm. The ORB feature detector will detect fast corner points in each layer of the image Gaussian pyramid, and use Harris corner scores to evaluate the detection points to select the highest quality feature points. ORB features have scale invariance, rotation invariance, and certain affine invariance. This time, the high-performance embedded platform we used is JSON TX2. It is a powerful multi-core mobile SoC released by NVIDIA in 2017, mainly for smart terminal devices, such as smart robots, drones, unmanned driving, smart cameras, and portable medical equipment. For the front end, based on the feature point method, the main processing procedures are image feature extraction and matching. They consume more than half of the computing resources and are calculated for images. So, the two parts are particularly suitable for parallelization. In order to verify that the GPU parallelization method used in this paper can effectively accelerate the processing speed of the front end, the parallelization method is tested on the UROC MAV dataset. The datasets, those names started with MH, are the video shot indoors, easy, medium, difficult, represents the complexity of the scene in the video. As the complexity increases, high-speed moving scenes with strong lighting changes, and scenes with fast turning will appear in the video. These scenes will affect the accuracy of the estimate camera movement trajectory. During the experiment, the time cost of executing each set of datasets was recorded under the conditions of only using CPU and using GPU acceleration respectively. The time unit is minutes. From the results, the time cost of running the dataset after using GPU parallelization on TX2 is greatly reduced, reducing the time by about half. Therefore, the use of GPU parallelization can significantly improve the processing performance of the Visual SLAM front end. Visual SLAM needs to process a large number of image data, so the performance requirements of computing hardware are relatively high, which limits the application of Visual SLAM on embedded platforms. In this paper, we study the front-end problem of Visual SLAM based on embedded platform, and then we propose front-end parallelization scheme. Finally, the Visual SLAM system was implemented on the embedded platform through GPU parallelization, and the effectiveness of the system was verified through the datasets. The Visual SLAM is a huge and complex project. Due to the time constraints, we have not done enough research on it. Future work can be started from the following two aspects. Use customized FPGA to execute Visual SLAM algorithms. This approach may make the execution efficiency of the algorithm higher and make the system have better real-time performance. When the camera moves too fast, the image texture information collected by the camera is not rich enough, and the scene illumination changes drastically. The visual slam will have large estimation errors or data loss. Therefore, the second aspect is use multi-sensor fusing to compensate for the disadvantages of visual sensors. The above is all the content I present. Thanks for watching this presentation.
Hello everyone, we are from Chengdu University of Information Technology. Our paper's title is Image Extrapolation based on Perceptual and Style loss. Image extrapolation, a specific application of image compilation, utilizes fragments of images to infer extensional parts and finally generating the whole picture. It can be mainly used on texture synthesis, panorama synthesis, and video expansion. However, it remains a challenging problem than image painting due to two main issues. First, fewer image proximity information can be used to infer the unknown regions. Second, the extrapolative results must be semantically plausible and visually vivid. This is our network architecture. Our network consists of two parallel passes, the reconstructive path and the generative path. The encoder-decoder network is used in our method. Especially, the encoder extracts high-level abstract features of the image, and the decoder utilizes abstract features to upsample a reconstructive image. Moreover, both the encoder and the decoder are collected by race block. The middle race block realizes the inference network function. This could generate the mean and the variance of VAE for the decoder sampling in the latent space. To improve the stability of training procedure, we apply AAA scan that uses the least squares loss. In addition, the structure of the discriminator is similar to that of the encoder, and we use the global discriminator to score the whole image. This could grasp the overall quality of the image. First, let us to see the perceptuals. The perceptuals extracts the features from both generative images and original images through the pre-trained VGG network, and restrains the features of those images by the L1 normal, since forcing the generative results to perceptually resemble those labels from pre-trained network. The perceptuals could improve the quality of the extrapolative areas. Perceptuals is to compare the features from the convolution of original images and the generative images in the VGG network. This aims to make the extracted high-level feature information, such as the contents and the structures of the images, as close as possible. It also means that the network is perceiving the image. In the training of GAN network, perceptuals can make the feature map of the generative image close to that of the original image. Finally, assists the image generation and improves the quality of generative images. The next is stylus. Stylus is similar to perceptuals. We also use the pre-trained VGG network to extract features from both generative images and original images. However, the gram matrix of extracted features is further calculated. As restraining the gram matrix of the features, the overall style of both generative images and the original images could be as close as possible. Finally, the quality of the generative images also can be improved. Gram matrix calculates the inner product of any k vectors in the n-dimensional Euclidean space. It can be regarded as a covariance matrix without subtracting mean between different feature maps. In the convolution network, the shallow network extracts low-level features of the images, while the deep layer network extracts high-level abstract features. Those low-level and high-level features are more like the overall style of an image, which determines the real attribute of an image. By calculating the gram matrix of those feature maps, the correlation between pairwise engineer vectors can be estimated. In the training procedure, owing the style of the generative images can be gradually close to that of original images, the quality of generative image could be improved. We evaluate our model in Paris Street View dataset. Figure 1 shows the extrapolative results generated by PIC and our method, which could be used to visually estimate those results. In Figure 1, say the PIC generates the results with distorted structures and even residual shadows in the extrapolative regions. Moreover, the results of PIC also exhibit slightly blurriness and unnaturalness. In Figure 1, D and E, we add stylus alone or add stylus and perceptuals at the same time into PIC. As a result, the generative results have some improvements. Our model could basically eliminate the parts with residual shadows in PSA and force the generative images to be closer to the style of ground truth. Table 1 and 2 show the quantitative results of different methods and place 2 and Paris Street View. Those results of quantitative matrix show that after adding style loss and perceptual loss, the generative images could be improved in some degrees. Table 1 is a quantitative matrix of 20,000 text images and place 2. The IS matrix increases by 0.09 and the FID decreases by 2.94. Thus, it shows that our methods could effectively improve the diversity and clarity of the generative images. Meanwhile, RMSE and L1 matrix decrease by 1.45 and 0.65 respectively, indicating that the overall pixel differences between the generative images and the original images are smaller. However, owing to the limitation of the 100 texture images of Paris Street View, we only evaluated the SSIM and RMSE. Furthermore, the SSIM and RMSE and the Paris Street View are also better. In addition, we have also implemented the comparative experiments and the IOG method. Table 3 and 4 show the quantitative results of different methods and place 2 and the Paris Street View dataset. The experimental results and the place 2 dataset show that our method increases by 0.57 and 0.29 in IS and PSNR respectively, and the FID and the LE loss decreased by 5.7 and 1.32. Thus, it proves that the style loss and perceptual loss can improve the quality of generative images, and it can also improve the clarity of naturalness of the extrapolative results. Moreover, the SSIM and the RMSE matrix and the Paris Street View dataset are also improved. Concluding, we proposed a new image extrapolation method. It combined the perceptual loss with style loss. After training and testing on the commonly used image extrapolation dataset, experimental results show that our model could produce fine textures and natural contents for the missing images. In addition, no matter qualitative or quantitative comparison, our results could exhibit better than those methods. In the future, we will continue to explore the relevant aspects of image extrapolation and further improve the quality of generative results in the field. Thanks for your listening.
Okay, let's start. Hello everyone, my name is Chen Yuan. I come from the University of Science and Technology, Beijing. Today I would like to share my conference paper to all of you. The name is Robust Frequency Estimation and Additive Mixture Noise. Here is the outline. First, I would introduce the background of my research, including the applications. Then I would present the details of the proposed method. Then I would like to show the simulation results, which indicate the accuracy of the proposed method. Finally, a conclusion can be drawn. One important application of our work is called a cosmic microwave background. Let's see this picture. This is a very clean CMB picture. From this picture, the researchers ensure the Big Bang of our universal. At the beginning, actually, the data observed by the Planck mission is composed by three parts. First is a CMB. Then it also includes the extragalactic point source and the detector noise. For these two parts, they can be modeled as outliers and a Gaussian mixture, a Gaussian noise. Then we can see this model. If we want to recover the clean CMB, we need to remove the outlier and the Gaussian noise at the same time. That means this work will be very challenging and meaningful. That's why our research focuses on the noise, which is additive mixture in time domain. Then I would like to state the signal model before we state the problem. Actually, in our signal is very simple signal. We consider a sinusoid signal, which is a single tone, which is in presence of the mixture noise. Here, we consider the mixture noise, which is additive Cauchy and Gaussian noise. As we can see this model, Yn is the observed data, A is amplitude, omega is frequency, phi is initial phase. And we can see the amplitude, frequency, and initial phase are unknown. And for this noise, we can say this noise is a mixture of Cauchy and Gaussian noise. And for the Cauchy noise, it has an unknown dispersion gamma. And also for the Gaussian distribution, it has an unknown variance sigma square. That means in our work, the task will be to obtain the theta, which includes the A, omega, phi, gamma, and sigma square from the observed data. As we can see here, the initial phase is and the frequency are unknown. The frequency and the initial phase is nonlinear. Therefore, to simplify the we introduce A1 and A2. After we introduce these two parameters, the nonlinear of phase can be changed into the linear, which simplifies our problem. In this case, our task will be changed into estimate the linear problem A1, A2, nonlinear problem omega, gamma, and sigma square. And before we start our estimation problems, we need to also back to our noise. To study this noise, we should to study the PDF of this noise. And then we can say first two equations are the Cauchy and the Gaussian distribution equations. And then we can derive the PDF of our ACG noise and can be calculated by their conclusion. Say this equation. And this equation is also called the Voigt function. We can see the Voigt function includes the van der Waals function, which is very complicated. We can see it includes the complex number integral. Therefore, in this case, the normal estimators cannot provide the accurate estimation because the PDF of this noise is very complicated and cannot find some regular things about this. And also, the maximum likelihood can provide the accurate estimation. However, for the maximum likelihood estimation, the PDF is very complicated. Therefore, this method will suffer from the high complexity computation, which is not a good choice. Therefore, to find an estimator which is accurate with lower complexity computation, we focus on the Bayesian estimation. For the Bayesian estimation, we can say differ with our previous estimators. For the Bayesian method, it considers the annual parameters, the posteriori of annual parameters. For the posteriori annual parameters, it composed by the Voigt function and the priori of unknown parameters. We can say here, for the posteriori of the annual parameters, according to Bayesian theorem, it has some form like this, something like this. Then, if we want to derive the posteriori of these annual parameters, as we have know the PDF of observations, we need to define the posteriori of annual parameter. And we can see here for the annual parameters, for A1 and A2, we suppose they follows the Gaussian distribution. And for the omega, it follows the uniform distribution. And for the gamma and the sigma square, it follows alpha beta distribution. And some parameter setting are shown in the below. After we know the price of annual parameter theta, and also know the PDF of observations, we complicate it. That's the Metropolis-Hastings algorithm. Then in our problem, we choose the Gaussian distribution as a proposed distribution. And see here, we can say the noise is here. The proposed covariance sigma is very important because its entrance of this proposed covariance is very important because for the small values, it will make the slower convergence but small fluctuation. For the large variance, it makes the faster convergence but has oscillation around the correct value. Therefore, for the MH algorithm, the very important thing is how to define the proposed covariance. In our method, we propose a new method to choose the proposed covariance. As we can see here, for the first P samples, we first to serrate the first P samples, because usually for the first P samples, the proposed PDF is not stable. Then from the P plus 1 to the K plus P, then we can utilize a slide window, and then we choose the L samples, and from the if we want to estimate the theta K plus 1, then we can consider theta K previous L samples minus the theta K minus 1 previous L samples. And the expressions can be shown in the PowerPoint. And maybe the steps of our proposed method can be shown like this. First, we initialize the theta. Then we generate the P samples using the MH algorithm with fixed proposed covariance. Then from the P plus 1, we calculate the proposed covariance using our method. Then continue to sample from this MH algorithm. Here is the simulations. According to the right-hand parameter settings, we can say in our proposed covariance matrix, then the samples can oscillation around the true values with a very little values. Then here is the gamma and sigma square, also approximately correct. And finally, we can say the comparison of the mean square error of omega versus the gamma. Here we can say the comparison with L1 norm estimator is also provided. We can see here, compared with L1 estimators, our method can attend to CILB very well. That means our method is accurate. And finally, I would to draw conclusion. And the estimation of the sinusoid signal and the additive Cauchy-Gaussian mixture is studied. Then, based on the posteriori of unknown parameters, we utilize the Metropolis-Hastings algorithm. We also proposed a new calculation method of proposed covariance matrix. And finally, simulation results show the optimality of the proposed method in this mixture noise. Okay, that's all. Thank you for the listening. So, any questions?
Good morning, good afternoon, and good evening, everyone. It depends on where you are. Thank the organizing committee and the EAS conference management team to prepare and organize the conference. Thank the reviewers for taking the time to handle our paper and give us valuable advice. First, I would like to make a brief self-introduction. I'm Ming Zhong, an associate professor in the College of Optoelectronic Engineering, Chengdu University of Information Technology. The title of this conference paper is Composition of two Fourier transform measured in Modulation measurement Profilometry, and I will give you a report on behalf of all the authors. Where is Chengdu University of Information Technology? It is located in Chengdu, Southwest China, and welcome to our university. This project was supported by the National Nature Science Foundation of China, Sichuan Education Department project, and college student innovation and entrepreneurship training programs. Views expressed in this talk are those of the authors and not necessarily those of the above foundations. This is the outline. It includes 6 sections. For the first section, Introduction. 3-dimensional surface shape measurement with the virtues of non-destructive, non-contact, high resolution, and high speed has become attractive to many industrial meteorological, RNA scanning, biomedical engineering, face recognition, automatic manufacturing, and electronic products. The optical 3-dimensional shape measurement based on the trigonometric measurement principle has the feature of high measurement accuracy. However, this technique has an inherent problem with shadow because there is a certain angle between the project and the detection axis. Therefore, for the text object with steep surface, how do we accomplish measurement requirement? Some vertical measurement techniques has been proposed to address this problem. Modulation measurement profilometry is distinct from the optical 3-dimensional shape measurement based on the trigonometric measurement principle. applies a configuration with the feature that projection axis coincide with the detection axis, or the detection direction is the same as the projected direction. According to the image fringe shows in this picture, when project the image of the grating to the specimen surface, the clearest fringe will be produced on the focal plane. Correspondingly, the modulation value will be the largest as the distance of the image plane to the focal plane increases. The image becomes more and more blurred. Therefore, the modulation value will gradually decrease. Based on that, a relationship between the modulation and the image plane position can be formed as shown in this picture, which is the basis of the modulation environment profilometry. This is the system configuration. For this technology, the spatial distribution information of specimen is encoded into the fringe defocus. So modulation value instead of phase information in the fringe pattern is required to be analyzed to accomplish the reconstruction. The light intensity distribution of the fringe pattern on any plane can be expressed as this equation, where ID represents the light energy distribution of the T's fringe. There are two methods to extract the modulation value of the fringe pattern: one-dimensional Fourier transform method and two-dimensional Fourier transform method. Before the calculation, let's simplify the equation. Use phi to replace this part. For the one-dimensional Fourier transform method, the calculation result is completed from an angle of an intensity curve formed by eponymous pixels from the captured image. Points at the same position are extracted from these images to form an intensity curve. Do Fourier transform method. On this curve, we can get its spectrum, and it is expressed as this equation. The utilization of the proper filter can make the acquisition of useful fundamental content come true, and then do the inverse Fourier transform. Modulation value for each fringe and this position can be finally obtained by taking the absolute value of the result. Therefore, it is a kind of point-to-point opposition. For the two-dimensional Fourier transform method, the result is obtained from the perspective of the entire two-dimensional image from the series of captured fringe patterns. For these fringe patterns, any image in fringe domain can be expressed as this equation. Select an appropriate filter window to extract the fundamental frequency part, and then apply the inverse Fourier transform. The modulation value can be obtained by taking the absolute value of the obtained result. When make a comparison between the two equations, it is apparent that they are the same, which means that both of them can get the modulation of the fringe pattern. These pictures show the flow chart of the two methods, and the two results do not represent actual reconstruction, but only a schematic diagram. We will discuss their results later. For this flow chart, we know that one-dimensional Fourier transform method is a kind of point-to-point operation. It can terminate the fluence from the operation of its neighbor pixel. That is, the operation of each pixel in the entire fringe pattern is independent of each other. The frequency spectrum of curve by one-dimensional Fourier transform measured is simpler than that of an image by two-dimensional Fourier transform measured. Moreover, it is easier to extract useful fundamental frequency information to retain more details of the specimen. However, for two-dimensional Fourier transform measured, we know that it is a global analysis method. The modulation value of any pixel in the fringe pattern is extracted by taking advantages of information of pixel in the entire two-dimensional fringe pattern. Therefore, even if a pixel in the fringe pattern has no data, a modulation value for this pixel can be estimated based on the information of surrounding pixel, which implies that the sensitivities of this method is not high enough. Besides, the application of filtering operation makes this method fail to retain the details of specimen, which will smooth the steep edges, corners, bring down a steep slope. To prove the above analysis, we first performed a simulation, respectively measured two kinds of objects. Object with a smooth surface and object with a steep surface. 160 fringe patterns was used to obtain the modulation distribution. A shows the texted object. B shows the 60th fringe. C and D are the modulation value for B, respectively obtained by one-dimensional Fourier transform method and two-dimensional Fourier transform method. One could observe that there are many small spots in C, and the edges in D is blurred. The reconstruction results error distribution for the two approaches are respectively shown in A to D. For the object with a smooth surface, the mean square error are 0.353 millimeters by one-dimensional Fourier transform method and 0.144 millimeters by two-dimensional Fourier transform method. While for the object with steep surface, the mean square error are 0.351 millimeters by one-dimensional Fourier transform method and 3.543 millimeters by two-dimensional Fourier transform method. These mean images show part of the reconstruction. Obviously, it proves our analysis. One-dimensional Fourier transform method can retain more details, and a two-dimensional Fourier transform method can get a more smooth surface. To further improve the above analysis, the phase of material is applied to have a test, and we can get the same conclusion. To get more efficient modulation and improve the measurement accuracy, three aspects should be taken into account. First, period of the grating. The period of the grating should be small enough. Second, interval and range of grating movement. The distance of each movement for the grating should be appropriate small. The entire range of grating movement should be large enough. Finally, transition platform. A closed-loop step monitor control system utilized in the system will improve the measurement accuracy. Conclusion: one-dimensional Fourier transform method can retain more details of the measured object, while the surface of the reconstruction will coarse. Two-dimensional Fourier transform method can get a smooth surface, while the result will lose many details. So, one-dimensional Fourier transform method is suitable to measure the object with sharp variation in height or steep surface. and a two-dimensional Fourier transform is more appropriate to measure the object with smooth surface. That's all the content of my report. Thank you very much for your attention.
Ladies and gentlemen, good afternoon. I'm very glad to have this opportunity to be here to attend the conference. My major is mathematics. The topic of my presentation is stability analysis of quaternion-valued neural network with non-differentiable time-varying delays and constant delays. My presentation will include these 5 parts. First, the background of our research. Second, the research status. Third, the vital contributions in this paper. Next, the main results we have proposed in the paper. And the last, simulation example. In the first part, I would like to introduce the background of our research. Let me just talk about neural network firstly. Neural network is research's hot spot in recent years. It overcomes the limitations of traditional computers in processing unstructured information. And at the same time, it has been widely used in signal processing, pattern recognition, state estimation, associative memory. Next, this equation x equal xr plus I xi plus xj xj plus k xk. This equation is the definition of quaternions, and this is the Hampton's rule which quaternion must obey. We can realize that quaternion does not satisfy the commutativity law of the multiplication. If a neural network's state connection weight matrix, activation function, and external input are all defined in the quaternion domain, we could say it is a quaternion-valued neural network. There are irreplaceable advantages of real-valued neural networks. We could also say RVNN and complex valued neural network, CVNN, in high-dimensional data processing, since the definition of quaternion. And this is why we choose QVNN as our research direction. Because of the Hampton's rule, there are less research results now. In second part, let's talk about research status. Before the 21st century, Hampton proposed quaternion in 1843. The subject of artificial intelligence, AI, is proposed formally in 1956, and in mid-19th, the neural networks model is constantly improving with the development of neural network technology. In 1995, the energy function of Heterogeneous QVNN model is studied. Japanese scholars defined the Hopf field and the quaternion field, proposed related models and energy functions in 2005. Chinese scholars defined mu stable in 2006. The stability of QVNN model with discrete time-varying delay is analyzed by direct method in 2018. The stability of QVNN with time-varying delay and time-varying uncertainty path is analyzed by direct method in 2019. Next part is vital contribution of this research. First of all, we discussed the global mu stability of the QVNN model with non-differentiable discrete time-varying delay. So it is closer to practical application. And then we investigate the QVNN model as an entirety, not decompose the QVNN model into 2 7NNs or 4 RVNNs. We avoid the problem dimensional increase. There are vital contributions in this paper. Okay, now we move to the part of main content in the paper. The QVNN we discussed has least constant delay and non-differentiable discrete time-varying delay and distributed constant delay, which is closer to practical application than the QVNN with differentiable time-varying delay. We obtain two results, including the equilibrium of the QVNN model is unique, and the QVNN model is global mu stability by considering the QVNN model as an entirety. The uniqueness of the QVNN's equilibriums is obtained by using Hermite-Formyson mapping theorems and quaternion-valued linear matrix inequalities. We could also say LMI. And in order to get through the results, we made some preparations, like Assumption 1 and Lemma 1. If Assumption 1 holds, and there are positive matrices U and positive matrices J1, J2, J3, and the matrix sigma, just like this, we could say the equilibrium of the QVNN is unique. Let's consider the continuous map Hx. Hx equal minus dx plus agx plus bgx plus tau cgx plus v. We first proved that the continuous map Hx is an injective by contradiction, just like this. And the norm of continuous map tends to infinity is improved. So, a unique equilibrium point of the QVNN model is proved. The global mu stability of the QVNN is obtained while applying the derivatives of the Lyapunov functional as well as quaternion-valued LMI. A new Lyapunov functional is constructed based on the delayed state feature. And in order to get the result, we also made preparations like definition 1. If the following conditions are all met, the QVNN model is global mu stability. We use Lyapunov function v1t plus v2t plus v3t plus v4t plus v5t, just as below. We obtain the result based on the derivative of Lyapunov function along the trajectories of the QVNN model. This is v1t. And v2t. v3t and v4t. And this is v50. So the QVNN model is global mu stability proved finally. Now we come to the last part, simulation example. Considering the following QVNN, which with leak constant delay and non-differentiable discrete time varying delay and distributed constant delay. We randomly define criterion matrices of the QVNN, just like the figure 1. This is solution of LMI by using MATLAB. There are pictures of QVNN's trajectories by using MATLAB. We test and verify the validity of the conclusion, finally. That's all for my presentation. If you have any question, please feel free to contact me. And here is my email address. Thank you all.
Hello everyone, my name is Yuan Chen. I come from the University of Science and Technology, Beijing. Today I would like to introduce my new paper, which is titled IAA Spectral Estimation in the Selective range. Actually, IAA, which is short for the Iterative Adaptive Approach, has been proposed to be a high-resolution spectrum estimator. The main idea of IAA is reformulating the nonlinear frequency estimation problem as a linear one, with the parameters being updated iteratively according to the weighted least square. Since the derivation of IAA is based on grid search in a fixed frequency range from 0 to 2 pi, the accuracy of the IAA is limited by the number of grids. Therefore, in this paper, we're proposing two new generalized IAA, which can work well in a flexible frequency range, so that the performance can be improved in the same grid points. Simulation results are also included to demonstrate the support of our proposed method. In my following lecture, I would like first give a brief review of IAA algorithm. Then, the main idea of two proposed methods, which are named SIAA1 and SIAA2, are also provided. Computational simulations in section 4 demonstrate the accuracy of proposed methods. Of course, finally, the conclusions can be drawn. Before start the details of our proposed one, we would like to review IAA. Actually, to simplify the problem, in our paper we only consider 1D uniform sampled sequence. And here we can say, if we set up a frequency component which is expressed as capital A, here the matrix A includes the frequency B, which is equal to the 2 pi multiplying k over capital K. Then we can describe the observation in time domain, utilize expression in frequency domain X. And then, of course, as the observation, this data is mixtured by the noise. Therefore, from the data model in the equation 1, our task is to estimate the frequency, the spectrum or the frequency coefficient corresponding to the observation. Then, since here X, the length of X is much larger than the length of y. This is an underdetermined problem. Therefore, different with previous work, IAA served the equation 1 by minimize the cost function, which is to make the observations minus the column vector multiply the xk, which can be shown in the equation 2. Of course, we can say the error between the observation and this vector column A is in fact dependent on each other. Therefore, to obtain the accurate results, IAA utilizes the weighted least square. Of course, here the weighting matrix is in fact the covariance of this error, which is composed by the IAA interference and noise covariance matrix. Since we don't know how to calculate the IAA covariance matrix capital R, then we employ the expression in the data model to express the R. Utilize the spectrum value X. Then, as we can say in this equation, the weighting matrix contains the unknown parameter X, while X is also unknown. Therefore, to solve the problem, I proposed to express the xk with to iteratively updated this IAA covariance matrix, and with the use of matrix inverse lemma, we finally can derive the estimates of IAA. Is in fact components by the vector column vector and the IAA covariance and also the observation, which can be shown in the equation 7. Here we can say as the IAA covariance R is composed by the capital P corresponding to the full frequency range. Therefore, directly change the values of capital A cannot obtain the correct problem. Therefore, this motivates us to think about can we calculate the covariance matrix using another method? In this case, as we have a priori knowledge where the signal locates in a selective range. Therefore, we can decompose this original data model into two parts. First part is the XS in the selective range. The second part is X, which is outside of the selective range. We can say expression in equation 8. Therefore, we can say, as we have known, the signal locates in this selective range. Out of this range, it only composed by the noise. Therefore, here we're trying to reformulate this the second part in the equation 8. Then we can see here, we can compose or regard the second term as a new noise. For this new noise, of course, we can still have we can still following the main idea of IAA. Then we can also to calculate this. Here to calculate the covariance matrix R, In the first proposed method as the IAI, we try to solve the problem in the frequency range. That means we try to calculate or reformulate or reconstruct the X OS1 and OS2. Utilize the S, which is the values in the selective range. Here we can say, as we have known, the power are not changed in time domain and the frequency domain, which is the energy conservation law. Then we can build this relationship, and also employing the definition of this variance, we can derive the second equation. Then finally we can express XOS1 and XOS2. Then the steps of SEIA1 is to first implement the integral frequency matrix A and the frequency matrix AS, which is located in the selective range. Then setting an initial value of XS, XOS1 and OS2. For example, all size to 1. Then reshaping vector P and then R to utilize the equation 4. Estimating XS using the solution 11 and compute the values of X outside of a selective range using equation 12. Then iterated the steps 3 to 5 until the relative error is intolerance. Then after iteratively convergence, we can finally obtain the accurate problems. And the other proposed method is considered in time domain. That means we regard outside of all the things outside of selective range as noise. Then, according to the definition of this noise, we can finally derive a covariance sigma square. And this sigma square can be calculated by the equation here. And of course, we can say that the steps of SEIA2 is first implement the matrix, then setting an initial value of the spectrum values in the selective range. Then estimate the sigma square using the equation 12, and the construction the vector PS, and then the covariance matrix R use equation 13. Estimating the XS using solution 11, and finally to iterate the steps from the 3 to 5 until the relative error is intolerance. Therefore, after we have introduced these two methods, I would like to show you some simulation results. Here the parameter here we consider a signal model, which is two sinusoid signals with a mixture noise QN. Then we can say we set the parameter setting as shown here. Then figure 1 shows that since we utilize a cosine function, which refers to the real tone IAA, we can say what we shown is only from the 0 to pi. Well, I still must to calculate from 0 to 2 pi, which is a waste of the method. Compare these two methods, we can say our proposed method is correct. Then we can see finger 2. Finger 2 actually is to consider two 1D complex tone with original IA and SEIA1 and 2. Here we can say the upper first two fingers is IA and IA with axis, because here we only show two peaks, so that we can study more details of them. Then we compare the SEIA and SEIA2 with the original IAA. Say, actually, the pictures are similar to each other. And of course, the computational time in the of three methods are also calculated. We can say with the same grid points, our proposed method has much lower computational time than the original IAA. And finally, we would like to draw a conclusion. In this paper, we consider to generalize the version of IAA. After we propose two methods, SEIA1 and SEIA2, which can calculate the spectrum, the high-resolution spectrum in any flexible range. Then we can say the simulation results demonstrate our proposed methods are accurate and suffers the lower computational time. Okay, that's a main idea of this IA method. Thank you. And any questions? Hello everyone, my name is Yuan Chen. I come from the University of Science and Technology, Beijing. Today I would like to share my paper, which is named Optimum Parameter Estimation and Additive Cauchy-Gaussian Mixture Noise. Actually, from this title we can say our research is focused on a new mixture noise, which is named the Cauchy-Gaussian mixture noise in time domain. For this type of noise, it's more complicated than the mixture in PDF domain. This is because for this mixture, the PDF of this mixture noise is usually the convolution of two PDFs. Therefore, the PDF function expression of this Cauchy-Gaussian mixture noise is much more complicated than the PDF mixture. In the following lecture, I would like to first to give you an application of this type of noise. Then I would like to introduce my algorithms estimators for the constant estimation. Then the simulation results are also included to indicate the accuracy of our proposed methods. Finally, a conclusion is drawn. First, I would like to introduce an application which is a cosmic microwave background picture. Actually, this CMB picture is a relics of the Big Bang. We can say in the picture, the clean CMB is in fact recovered from the raw data observed by the Planck. For the raw data, which is also have the name of observations, which is composed by three components. First is clean CMB, which following Gaussian distribution. The second is extragalactic point source, which is modeled as impulsive noise. And thirdly, the detected noise is also included, which follows the Gaussian distribution. From the expression of this observation, we have known that recover CMB from this raw data is much challenging and meaningful. We say challenge because for this raw data is composed by the impulsive noise, not only the impulsive noise but also Gaussian noise. The meaningful because the DMP recovery will help us to find the origins of people. Then to start this type of noise, we investigate a simple estimation problem, which is a constant estimation in the presence of this mixture noise. We can say the data model in equation 4. Here we can say this observed data is composed by the constant and the mixture noise, En. The En is also called the Cauchy-Gaussian mixture noise, which is mixed by the IID Cauchy noise with medium gamma and IID zero mean Gaussian noise with the variance sigma square. As we have known the PDF of these two types of noise, which are shown in equation 5 and 6, we have known the PDF of this mixture noise is calculated as the convolution of this PDF. After some complicated calculations, we finally know that this type of mixture noise, the PDF of this mixture noise, can be expressed by the van der Waals function. Shown in the equation 9, we can say, very complicated, right? Because here includes the imaginary part, it also have the complex integral. That's why we say for this noise, it's very challenging work. Of course, here our task is to estimate the constant from the observations. Here, as we have known the PDF expression of this noise, in our first month, we would like to utilize maximum likelihood estimator to obtain the estimates. And to generalize the problem, we consider two scenarios. First, the sigma square and the gamma are known, and the second scenario is both of sigma square and the gamma are unknown. First, we can say in the known case, here, since the PDF of mixture noise is known, we can express the PDF of the observation Yn as equation 10. Then, employing the maximum likelihood estimator, we can construct the cost function of this estimation problem. Then, finally, we can utilize the Newton's method to estimate this constant. We can see here, equation 14 to 17. It includes van der Waals functions and also includes the first and the second order deviation of this van der Waals function. Actually, in our first month, these expressions are very suffers very high computational complexity. That's why it motivates us to propose another method in the following. Before we introduce another method, we also need to consider in the second case, which is unknown sigma square and gamma. Here we can say, since we have known the characteristic of the mixture noise, then we can express the characteristic function of the observation for 18. And of course, we have so many data. Therefore, the numerical characteristic of this Yn can be expressed in 21. Then, if the number of data are enough, we can build the relationship between the magnitude of characteristic function and the numerical characteristic function. Therefore, we reconstructed this expression, utilize the cost function, something like this. Then, finally, this problem can be solved using the subgradient method. After we have estimated the gamma and sigma square, the constant can be estimated according to the previous idea. Actually, here we have known that although MLE has a high accurate performance, this method suffers from high computational complexity because the complex integral in van der Waals function is very complicated. Therefore, to reduce the computational cost, we consider to simplify the PDF of this mixture noise. Therefore, in previous research work, people found the Voigt function or the van der Waals function can be expressed by the sum of PDFs of Cauchy and Gaussian distributions, which is called the pseudo-Voigt function. Here, the expression can be shown in 24. We can say the PDF of CGM noise can be expressed by the weighted sum of a new Cauchy and Gaussian distribution. Here we say the new because the density parameter are totally different with true noise. Then we can see the 27 and 29. The mixture coefficient is very complicated. Then still consider two scenarios. First scenario, known gamma and sigma square. We can replace the Voigt function by the pseudo-Voigt function. Then solve the problems with some simplified functions. Then in the unknown scenario, still the similar idea. We first estimate the gamma and sigma square, use the relationship between the characteristic function and the numerical characteristic function. Then, after we have obtained the gamma and the sigma square estimates, we can utilize the equation 30 to estimate this constant. Actually, we also studied the theoretical computational complexity of these two methods. For the MLE, actually, the number of flops is n cubic, while the M estimator with pseudo-Voigt is the order n. So we can say the computational complexity is much more lower than the MLE. Then, of course, we have derived the expression of this of the chromoral lower bound of this noise type. Then to study the performance of our proposed methods, we utilize the MSE to measure the performance. Of course, here we set the constant A is equal to 0.5 and scale the sigma square to produce different noise conditions. Then, all the results are based on 1000 independent RAMs with a data length of n equal to 16. Of course, here the L1 norm estimator and the chromoral lower bound are included as a comparison. So we can say figure 1 shows the MMSE of A in different sigma square. Of course, this is in the scenario of known gamma and sigma square. We can see here our two proposed methods can attend to CIOB. Well, for the L1 norm estimator, it has a gap. This indicates the optimality of my proposed method in the known gamma and sigma square. Of course, we have also studied the computational complexity versus different data lengths. We can say When the data length increased, the computational time of MLE increased exponentially, while the the M estimator with pseudo void gate and the L1 norm increased linearly. That means our proposed MEPV has much lower computational complexity than the MLE. Figure 3 shows the MSE of A in the unknown gamma and the sigma square. Here we can say still align with the results in Figure 1. Our proposed method can attend to CLB well, while the L1 norm estimator have a gap to the CLB, which indicate the suboptimal of L1 norm estimator. Then to draw a conclusion. In this paper, actually we study a mixture model. We study a mixture noise model, which is the sum of two popular noise processes, Cauchy and Gaussian distribution. Of course, with the PDF of this mixture noise, we derive the maximum likelihood estimator for the constant in the presence of this mixture noise. Of course, here to generalize the problem, we consider the known gamma and sigma square and unknown gamma and sigma square. Then to decrease the computational time of MLE, we also proposed a new M estimator, whose main idea is to utilize a pseudo function to express the PDF of mixture noise, so that the computational complexity can be decreased much lower. Of course, the computational simulation results show that both the MLE and M estimator of pseudo void gate has an accurate performance, and the M estimator with pseudo void gate has much lower computational time than the MLE. And of course, in the future, this study on additive mixture can be extended to the autoregressive model and nonlinear parameter estimation. That's all. Thank you. Any questions?
Hello, everyone. My name is Pablo Palacios. I am the first author of this paper called Analysis of Spectrum Detection and Decision using Machine Learning Algorithms in Cognitive Mobile Radio Networks. whose authors and main universities are exposed on the slide. The schedule for this conference is the following. First, I'm going to introduce a brief concept of this topic. Then, I'm going to explain the cognitive radio system model and the secondary and primary users models, mathematical models. After that, I'm going to present the proposed machine learning algorithms used in this research. Then the performance evaluation and numerical results are presented and discussed. And finally, some conclusions are presented. First, about the principal concepts. Cognitive radio is considered an enabling technology for 5G communications. For a communication system to be considered CR-based, it must fulfill a cognitive process, which requires 4 steps: spectrum detection, spectrum decision, spectrum sharing, and spectrum mobility. In the last decade, investigations regarding the cognitive radio topic have been oriented in the field of spectrum detection and decision. On the other hand, in the search for mechanics to mitigate problems in the spectrum detection and decision states in cognitive radio systems, machine learning algorithms have received a lot of attention from the scientific community. The context of future networks, most authors present a problem formulation and methodology of several machine learning algorithms in terms of effectiveness in the testing stage. Finally, the main contribution of this manuscript is the performance evaluation of the collision game theory, naive Bayesian classifier, sport vector machine, and decision trees methods applied and adapted to a single cognitive mobile radio network. About the cognitive radio system model, to evaluate the spectrum detection and spectrum decision, we use the standard machine learning algorithms, which is composed by numerous inputs, hidden layers with different numbers of neurons, and various output applies to cognitive mobile radio network, implemented to coexist with a primary wireless network composed of 2 state-of-the-art technologies, which are Wi-Fi and LTE. We suppose an area covered by cognitive mobile radio networks, like the proposed scenario, as we can see on the slide, composed of several primary users, and for the secondary network, we use the cognitive radio interwave paradigm, a secondary base station, and N secondary users. About the secondary user model, first, we use the SVD, singular value decomposition detection method, for the spectrum sensing. And we formulate, as we can see in the first expression, the spectrum sensing problem. Then, the spectrum status is given as we can see on the second expression. And finally, the occupants for the time slot it acquires the form of the third expression. This expression means the average of state of the spectrum between the used frequency bins. For the mathematical primary user model, the primary user status is represented as a IPU. This status for the I time slot can be chosen according the rules that we can see in the for expression. We can see there are three steps for constructing a classifier. Three principal steps, which are training the classifier, testing, and take the classification quality. Now, we're going to explain the proposed machine learning algorithm in the research. The first one is the coalition game theory. This algorithm has two phases, the cooperation phase and the secondary use transmission phase. The first step is the local detection, which is done using the singular value decomposition method. All the communication phases are in a Rayleigh fading environment. And the principal parameters are the probability of detection and probability of false alarm. Regarding the coalitions, which are four with some secondary users with particular parameters, particular features in common. And within each collision, a single secondary user is called as the coalition head, collects the sensing bits from the coalitions, and acts as a fusion center to decide on the presence or not of the primary user. Other parameters, important parameters for each coalition are the missing and false alarm probabilities, as we can see in expressions 5 and 6. The second phase is the secondary user transmission phase. In this phase, we assume a time division multiplexing, and then the transmission is divided according the secondary user contribution in each coalition. The second machine learning algorithm is the naive Bayesian classifier. This algorithm is named as the independent feature model because it does not consider the features' interdependence, and in this model, the total samples are contained in the feature vector for the time I. Furthermore, the samples are independent of each other because of every feature represents a specific frequency bin. The probability of SS sub I by using the Bayes theorem is defined as the expression 7. And finally, the goal is to obtain the class with the largest posterior probability in the classification phase. The classification rule is represent a optimization function, as we can see in the expression 8. Next one is a support vector machine. This algorithm results in a discriminative classifier with high accuracy. In addition, singular support vector machine tends to be resistant to overfitting, and generally, two types of classifiers in singular vector machine are presented in the literature. But in this work, for simplicity, we choose the linear singular vector machine. The training feature and response vector are represented as D, and by definition, two classes of support vector machine are separate, defining a hyperplane H. And finally, the model for the primary user EAI, is present in the expression 9. The last one is the decision tree. In this work, decision tree is represented with a classificatory approach, where the leaves of the tree define the class level. A benefit of decision trees is that they can handle interruptions and feature dependency. Regarding the decision made by this algorithm, it is made at each node internally, which allows the data division into two own subsets. The data is represented as follows in the expression 10. And finally, the primary user is a dependent variable, which is assigned by calculating the entropy of the feature, as we can see in the expression 11. The performance evaluation and numerical results are present in this slide. The principal system parameters, the technical parameters for the simulation, are present in the table. Each of the machine learning algorithms were implemented in a simulate community radio environment. To generate the simulations, we use the NS3 software. The machine learning algorithm curves were obtained through the implementation and simulation of the algorithms. The probability of detection versus signal to noise ratio and probability of false alarm versus signal to noise ratio are present as a cumulative distribution function for the machine learning algorithms, as we can see in the figures. Both figures, the algorithm that presents the worst performance is the naive Bayesian classifier, due to its features of not having complete information and making decisions based on statistics. Coalition game theory, decision tree algorithms have a similar behavior because the first takes a cooperative detection between nodes, and the second divides the decisions into subsets, which are similar processes for the system. Finally, the algorithm with the best performance is the support vector machine, due to its high precision and accuracy when recognizing the use patterns of frequency beams for detection. The classification quality as a function of number of samples is present in the figure on the left. As the number of samples increases, they have more chance to sense, and sensing accuracy improves. However, by increasing the number of samples, the algorithm have a greater amount of data to process and become slower. In the right figure, we observe the linear and increasing behavior of simulation time versus number of samples. The support vector machine algorithm presents slightly better performance than the other machine learning algorithm due to its simplicity of learning. Finally, some important conclusions are mentioned. Some machine learning algorithms implemented in the detection and decision stage of a cognitive mobile radio network have been analyzed and compared. We characterized the network structure resulting from the proposed techniques. Its stability and performance was studied and observed in terms of probability of detection, probability of false alarm, classification quality, and simulation time. And finally, simulation results showed that support vector machine algorithm compared with the other analyzed algorithms outperform the cognitive mobile radio network based on the parameters studied. Thank you very much. Thank you very much for your attention. Any doubt, any question, or emails are in the slide.
Hello everyone, I'm Fenghai Li from Beijing Technology and Business University. Today, I'm going to talk about learn to rectify label through kernel learning machine. This work is done by myself and my advisor Qiang Cai, Haisheng Li, and Shanshan Li. Image classification is a fundamental task in computer vision, which aims to distinguish the image categories according to their semantic information. For example, give a picture of a bear, then input into a classifier. And the last, we can get the probability of the bear. The probability is more higher than for the better classification. So normally we focus on maximizing the accuracy of image classification. And at the meantime, is widely involved in image real-world application, including face recognition, traffic sign detection, and brain image analysis. We began from considering lessons from the previous work. Convolutional neural network has exhibited strong learning capability on image classification. It can be thought as consists of two parts: a feature extractor and a softmax classifier. The feature extractor can be constructed deeply, so it can obtain strong representative capability for input images, and its dimension is high. And then the softmax classifier consists of a full connection layer. The parameter is enormous and often lead to redundant load and poorly trained model. But the softmax classifier has many limitations because of non-layer conditions. Then some work try to replace the softmax layer by some traditional classifier, such as supervisory machine or extreme learning machine. For example, a neural work introduced by Li, they consider import discrimination ability of feature by replacing softmax with extreme learning machine. They use CNN without softmax to extract strong representative capability feature, and then send to this feature to extreme learning machine and get a better accuracy compared with softmax. Let's explore extreme learning machine. Extreme learning machine is a single hidden layer feed-forward neural network which randomly chooses hidden node and output weight. Extreme learning machine tend to provide good generalization performance at extremely fast learning speed, and the hidden layer need to not between. In this work, it sends a high dimension feature to extreme learning machine and then gets the final result. However, due to the extract high dimensional feature, the training time of extreme learning machine is time consuming, which still remains a challenge. Motivated by above study, we consider a different view that tries to rectify label output of convolution neural network to a more correct distribution. Instead of a feature-based method, we will use the output of label of softmax layer, whose dimension is smaller than features, and in this way, we can save training time of extreme learning machine. In this example, the extreme learning machine can rectify the wrong elephant label to right bear label. We therefore propose a neural image classification approach that learns to rectify labels through kernel extreme learning machine. It includes into two phases: pre-classification and label rectification. In pre-classification phase, we put the image into a trained CNN to generate corresponding incomplete labels. And then in label rectification phase, the incomplete labels are rectified by kernel extreme learning machines high dimensional mapping. So, the final classification results are acquired. Our method have well general ability that can be integrated with many popular networks. And one technique for better results needs a softmax layer. So Why we need a softmax layer? Unlike the previous work, we add the softmax layer, which output is equal the image classes. Dimension is smaller than the output of feature extraction. Under the side effects, we can reduce training time of extreme learning machine about 4 times, but the accuracy is similar than Li's method. Next, we will show you our experiment result. To evaluate the efficiency of label rectification, we conduct our experiment on CV10 and CV100. We use extreme learning machine and kernel extreme learning machine to rectify the output of VGG readability. It can be seen our method can obviously promote convolutional neural network classification performance. From these comparisons, we can conclude the proposed method can effectively rectify incomplete labels output by convolutional neural networks. Compare with extreme learning machine. Kernel extreme learning machine has more potential for image classification task. In order to evaluate kernel learning machine is more suited to rectify the incomplete label. We compare it with other different classifiers, such as support vector machine or kernel vector machine. Previously, Li's method and kernel extreme learning machine are efficient in improving the performance of image classification, but other classification produce a negative effect on improving accuracy. But in contrast, experiments show that our method had the advantage of high training speed. So our method can better balance the efficiency and accuracy. Finally, we compare our method with the state-of-the-art method, and obviously, we achieve the best results. These are conclusions. To our best of our knowledge, this is the first time that a label rectification method is proposed for image classification. We present a novel image classification framework that combines CNN with kernel extreme learning machine, and it has well generability for different convolution neural networks architecture. Our experiments on public datasets also demonstrate our superiority on image classification tests. Thank you, that's all.
Hello, experts. My name is Huang Guo. I come from Neshan, a small city in western China. The city is famous for its Neshan giant Buddha and Omei mountain. The title of paper is Research on Image Enhancement Model Based on Variable Order Fractional Differential CLAHE. The authors of the paper are Huang Guo, Xu Ni, Chen Qingli, Zhang Xiuqiong, Wen Tao, Qin Hongying. The corresponding author of the paper is Dr. Xu Ni. There are two motivations for this paper. Image visual effects can be enhanced primarily through edge and texture enhancement or contrast enhancement. Image enhancement based on fractional differential can effectively enhance image details such as edge and texture using the weak derivative property of the zero-one order fractional differential operator. Image enhancement based on gray statistic involves the redistribution of light and dark pixels and to enhance the overall contrast of the enhanced image as well as the enlargement of the gray level dynamic range, thereby improving the visual effect of the image effectively. The main idea of this paper is as follows. To enhance the edge and the texture information for the image, enhance the contrast of the image effectively, and then improve the visual effect of the image. An image enhancement model based on contrast limited adaptive histogram equalization is corresponding fractional differential operator is proposed. The image enhancement model incorporates a fractional differential operator into the adaptive limited contrast image enhancement model, which can enhance the image contrast and effectively enhance the edge and the texture details of the image simultaneously. Fractional calculus theory is an intention of integral order calculus theory. The definition of fractional is realized using a difference scheme. Therefore, it is highly substable for processing the gray values of discrete pixels in digital image processing. Furthermore, the fractional GL definition is conducive to numerical calculations and can be regarded as the extension of the limit from the integer order differential. According to a similar definition, the definition of the n-order derivative of a continuous function f(x) can be deduced as shown in equation 1. Equation 2 can be simplified to equation 1. Figure 1 and Figure 2 respectively show the amplitude frequency characteristic curves of the fractional differential operator and the fractional integral operator based on the fractional GL definition. Direct observation shows that the fractional order GL calculus operator with a positive order can enhance the high frequency part of the single and the fraction order GL calculus operator with a negative order has a certain degree of nonlinear attenuation on the high frequency part of the single. To solve the block effect in the real-time problem of the traditional histogram enhancement model, carriers proposed a contrast-constrained adaptive histogram image enhancement algorithm. The CLAHE method consists of the following 3 steps. First, the image is divided into n and n image non-overlapping subblocks of the same size. Second, the histogram of the current image subblock is calculated, and the collapsed image histogram is determined according to the image reconstructed as shown in Figure 4. The number of pixels in the image block whose gray histogram is greater than the histogram clamping threshold is accumulated and stored in the exceeding threshold vector. Subsequently, the histogram is redistributed repeatedly to satisfy the sleeping threshold. Finally, the image subblock is proceeding using traditional histogram equalization. At last, the gray value of the pixel in the colorless region was determined according to the histogram mapping of the subblock. The specific interpolation method is expressed by interpolation formula. To enhance the edge and texture details of the image, effectively enhance the image contrast and improve the visual effect of the image. A model can bring the advantages of the fractional order, differential operator, and the CLAHE model is proposed here known as the variable order FCLAHE image enhancement model. There are 6 steps to description of FCLAHE algorithm. Step 1. The image is classified into 2 levels. Step 2. Calculate the subblock image eigenvalue. Step 3. Calculate characteristic value of secondary subblock image. Step 4. Determine the order of variable order fractional differential. Step 5. Construct variable order fractional differential enhancement model. Step 6. Set up FCLAHE image enhancement model. To verify the advantages of the FCLAHE image enhancement model proposed here, the current classical image enhancement methods were compared, including the Laplace image enhancement, traditional fractional order GL image enhancement, histogram equalization, and CLAHE method. The experimental results show that superior performance of the proposed method based on comparing the images obtained from different image enhancement methods and the texture characteristics of the image. Direct observation of the red circle part of the Babel image shows that the Laplace operator, fractional GL operator, and FCLAHE image enhancement model proposed here significantly improved the texture details of the written chair information of the Babel image compared with the HE and CLAHE image enhancement method. Direct observation shows that the method proposed here can enhance the detailed texture features of the image more effectively than other image enhancement methods, as well as effectively improve the local and overall contrast of the image. Direct observation shows that the CLAHE method demonstrated better overall and local contrasts than the Laplace method based on the difference and the fractional GL image enhancement method. Furthermore, compared with the image enhancement method based on statistical methods and CLAHE method, the FCLAHE method yield richer texture details and better visual effects. Direct observation shows that the FCLAHE method yield better textures than other classical image enhancement models. Moreover, it effectively enhanced the edge and texture features of the image while improving the overall contrast of the image. Direct observation shows that the FCLAHE method improving the low frequency, weak edge and texture details of the image more effectively compared with the difference or statistical image enhancement method. Moreover, it inhibited the ability of the non-local adaptive histogram operator to improve the local and non-local contrasts of the image. Consequently, the involution index of the enhanced image was better than those of other classical image enhancement methods. The conclusion of this paper are as follows. First, considering the advantages and disadvantages of the difference and statistical methods for image enhancement, a variable order fractional order CLAHE image enhancement model based on the existing fractional order differential image enhancement model and the classical CLAHE model was proposed. Second, the model uses the blocking mechanism of the CLAHE model, in which the current subblock image is divided into levels. The order of the fractional differential operator is determined by the linear weighted value of the fractional ladder, degree models, and the image texture measure of the current image subblock and secondary block images. At last, the simulation results show that the proposed FCLAHE method afforded different degrees of improvement compared with other classical image enhancement models, owing to the combination of the fractional differential operator and the CLAHE operator's excellent characteristics, whether in subjective direct observation or based on objective evolution data. My introduction is over. Thank you very much.
Hi everyone, I'm Wen Taoshi, a Chinese student from Chengdu University of Information and Technology. Today I will introduce an end-to-end method to get high accuracy face reconstruction. Our contact information has been written below. Please contact us if you have any questions. Today's speech is divided into 5 parts, namely Introduction, Related Works, Network and Loss Function, Experiment Results, Conclusion. Firstly, I will give you some information of computer vision and face reconstruction. Now, face recognition has been widely used in various fields. For example, during the COVID-19, various units has adopted face recognition to manage the entry and exit of persons, as shown in the picture. Two-dimensional face recognition is very mature, but the reconstruction of 3D face has always been considered as a major problem in the image field. Its problems include the lack of training set, and the reduction effect is affected by angle, illumination, and depth. It is extremely hard to get 3D model from 2D information. Here's an example of getting 3D point cloud information from a single picture. Our method does not rely on expensive equipment. I'll tell you something related to our works. In 1999, Blands and Viter proposed a 3D morphable model, also called as 3DMM, whose method can construct a 3D face map model based on 2D images. As pointed out above, the face is divided into the texture part and the structure part. The texture part coefficient and structure coefficient are shown in the equation. Alpha is the structure coefficient and beta is the texture coefficient. These two coefficients control the transformation of the face model, generate an average face model that can be deformed according to the images, and change the deformable model's coefficients to stretch the deform to obtain desired result. Later, in 2004, Blands proposed sparse facial feature point for model parameter estimation. Because of the application of deep learning, plenty of methods use neural network to regress 3DMM coefficient and perform better. 3D face reconstruction with region-based fit blending using mobile phone for virtual reality-based social media proposed a method to reconstruct a 3D face model from the obtained mobile phone. This method pays more attention to the shape of the model in order to be used for face recognition. Detected 68 face feature points and used them to calibrate the 4 areas of the face. For each region, find the best fitting model and further deform the combination of to find the best fitting model for each region. Then, these models are combined and further deformed to restore the original facial proportions. The article also proposed a method of texturing in the resulting model, in which the above-mentioned feature points are used to generate texture for the resulting model. Then, 3D morphable model as spatial transformer networks proposed a way to get UV map, which could store information in the 2D map. In 2018, reference joint 3D face reconstruction and dense alignment with position map regression network proposed to use 2D pictures with semantic information and now equivalently consider the weights of different points for evaluation. But the textured information of this model is rough. We directly regress a parameter of a 3D face from a single 2D face through the CNN network. Meanwhile, we need to emphasize the robustness of the method. Therefore, we need a dataset containing 2D faces and corresponding 3D information and also containing yaw angles as our training set. The 300W and 3D dataset contains large angle face images, which satisfies our requirement very well. We choose 300W 3D as our training set. To evaluate the superiority of the method, we manually noted the 81 feature points of some of the acquired pictures and showing them in the experiment results section. The UV map is a two-dimensional image that records the information of all 3D point clouds. We refer to proposed a method for constructing a UV location map. We design and use a hourglass network mainly borrowed from the fully conventional network and the residual network. According to the input color face photo, the UV position map is obtained from a single 2D face image. Each rectangle is a residual block representing future to ensure the dense geometric structure information of the face. The size of the UV map is 256, which can obtain a high precision point cloud. The network structure is shown in the picture. The network converts input RGB image into the corresponding UV image using encoder-decoder. The stride is 1, all kernel size is set to 4, and the renew function is used to activate. For loss function, since the UV map is obtained through the network, we can divide the face region. According to the difference of the region's future information, different weights are assigned to each region when calculating the loss. We divide the face into regions in the obtained UV space. Compared with the previous method, our distribute the weights more carefully according to the proportion. Experiments show that doing so can get better experimental results. The equation has been shown at the screen. As we said before, since the dataset requires both 2D pictures and their corresponding 3D semantic information, 300W 3D is selected as the training set because it contains 3D coefficient and the different angle visual pictures, which enables it to store 3D point cloud information compared with 3D DFA, DEFA, and PRNet. on the AFLW 2003D and Florence datasets. I show some results of our outputs. As you can see, including the front face and the side face, some input faces are captured by ourselves. We evaluate the method in large pose datasets by calculating the regularized mean error. The results show good robustness and well performance. Furthermore, we manually mark 81 key points in some photos and give the results at the rendering display part. In order to further study the performance of the method in this paper under different angles, some data are compared with the NME under small, different, and large deflection angles. The results are shown in the table. We use CED, cumulative error distribution, which is used to obtain the sum of all variables below the specific value to observe the experimental results intuitively. We evaluated the performance of our method on the AFLW 2003D. The results has been shown in the picture. Besides, to verify the effect of dividing feature regions, we compare the method of not considering feature regions. The allocation method is shown in Table 2, and the results are shown in the picture. Obviously, considering facial feature regions giving different weights to different regions can make our network better. The best way to evaluate the performance of the face model is to observe the reading result directly. We manually marked 81 key points. We display the outputs below. See the picture. Figure A is a reconstruction result of the front face, and the figure B is the reconstruction result of the side face. Even if the picture uses picture that includes a rotation angle, we can get satisfactory results. We provide a new idea for solving the 3D face reconstruction from a single 2D picture. This idea does not rely on expensive hardware equipment and complex networks and can fully return to the face features. Experiments show that this method has an excellent performance in 3D face reconstruction. In this paper, we show the CNN using the hourglass network structure to regress the UV parameters during the training process. Future points are added as a guide to obtain a robust face image. Meanwhile, an excellent facial feature extractor is introduced to visually display the rendering results. Even if the input image is rotated, excellent results can be obtained without being affected by the rotation. There still has many ways to extend this work, such as applying more accurate feature-aware area weights. Thanks for watching.
Hello everyone. Today I'm graduate to introduce to you my research about semantic waste environment. In the rest of this PPT, the structure is as follows. In part 1, we discussed the two main problems in SLAM systems. In part 2, we provided an overview of semantic SLAM and SLAM in dynamic environments. And in part 3, we post our whole system and discussed how to detect moving objects and produce semantic maps. And part 4 provides the results of our solution and ORB SLAM 2 on TUM RGBD datasets. At last, we give a brief consequence and discussion about our work. SLAM is a base code for many robot applications since it is popular topic in robot research. Thanks to SLAM systems contributing research by the research group, some advanced SLAM algorithms has achieved significant performance, such as ORB SLAM 2, LSD SLAMs. However, there are still some issues cannot be solved. For example, how to deal with the moving object in the environment. SLAM algorithms assumed a strong constraint about static environments where there are moving objects in the environment will cause the robot and aircraft will be significantly declined. What's more, how to make robots truly understand the surrounding environment. The typical SLAM measures only provide the geometric maps composed with point and plane, which does not consist of the surrounding environment semantic information. It cannot help with advanced tasks such as intelligent obstacle avoidance. The development of SLAM can be divided into 3 stages. The stage 1 is classified age. In this age, possibility in formulation is the subject of research. The measure in this age, like extending Kalman filter, and the most biggest challenge is efficiency and robust data association. The stage 2 is the algorithmic analysis age. In this age, the fundamental purpose of SLAM is observability, convergence, and consistency. In this age, the research focuses on sparsity towards to efficient SLAM servers, and the open source SLAM library are pushed out in this time. Now we have entered the stage 3. The stage is the robust performance age. The awareness of the robust performance, high-level understanding, resource awareness, and task-driven perception responds to the storm of this era. This table shows the main study about simulated maps in SLAM. It's clear that in earlier age, CRF is the main way to solve this problem. After the deep learning network has widely launched, more and more researchers began to use deep learning network to contribute to the semantic maps. For moving object detector is a classified problem. To solve this problem, the main stream measures are as follows. 1. Background foreground initialization. This technique assumes the system has a prior knowledge about the environment and using this information to segment static and dynamic features. 2. Geometric constraint. This technique that relies on geometric constraints like epiplanar geometrics. This is based on the fact that the dynamic feature will violate standard constraint defined by multiple view geometry for state sense. Optimum flow defines the apartment motion of the brightness apartment composed from two consecutive measures. Generally, it is corresponds to motion field in a margin, and through it can be used to segment a moving object. Motion constraint, standard SFS, and visual slams compose the motion of the camera by means of the A point of 5-point established is calculated without making any assumption on how the camera moves. 5. Deep learning for motion segment. This technique considers involvement of geometric transform as a learning problem, and it uses deep learning network to segment the object which can be moved. This table shows the main starting about moving object detect. As you see, the camera T means the camera type, M means the molecule, the S means the odors, the S means the camera state, the S means stable, and the M means moving, and the M means the camera's model, and the CT means the computation times. In the well application, the accuracy of the attitude established and the HAPS environment of reliability are similarly focused for environment robots. RB SLAM 2 as a lightweight SLAM system had extremely performance in static environment. We add a dynamic object detect module and a semantic module for it. As known, we have designed 5 through to control this SLAM system and 5 main modules. For the part of the dynamic environment, we place a real-time semantic segmentation network in the swap through and fit it out the things of dynamic target by combining the semantic segmentation and moving constraint check motion. This improves the robustness and accuracy of the SLAM system in dynamic environment. For the semantic maps part, we also design a through to build the tree maps. The semantic maps is realized in front of the banding with the semantic target. To get semantic information and moving objects in the environment, we use mask RCNN to perform the semantic segmentation on the margin and obliterate the object in the environment and the semantic information. Compared with other CNN network, MSR CNN has high speed and accurate. It can be divided dynamic or moving objects in the margin, such as people, animals, bike, car. Most objects in our lives are included his recognizable range. In the mask RCN network, we detect and process moving objects in the margin, but those objects are not in a real state of motion. They might also be static, such as car parking on the side of the road. If we remove the feature of the margin located on the object, through the negative impact of the motion, accuracy can be arrived, but we will also lose a large number of effort. This might cause the track of the SLAM system be lost due to lack of match features. Therefore, it is important to use the moment constraint to detect the true state of the object. geometric constraints are an effective way to determine the state of future motion. In this paper, we use the feature of epiplanar constraint to segment the moving and standing future of objects as shown in flags. The flag left is the transformation from point x1 to point x2 be defined by operation constraint in static presence, and the picture in right is the violation of the geometric constraint in dynamic environment. For map, the map used in SLAM systems are divided into point map or vector map. The advantage of point map, it can be efficiently generated direct from the RGB matching and does not request additional process. And the disadvantage of the point map is that first, the point map is usually large and carry too much unnecessary information, such as shadow and weakness. The point map cannot, and what's more, the point map cannot handle dynamic objects because the point map can only aid the point during the construct process. So, in this paper, we choose octree maps. The octree maps is more flexible and updatable than the point cloud map. Furthermore, the octree maps can be stored more efficiently and it is easy to navigate. In this paper, we use TUM RGBD dataset as the test data and compare our solution with the ORB SLAM. As it says, the flag in right is the evaluation of the absolute pulse error between our measured view and the real view. This data evaluated the overall consequence of our measured data with the true track. As it shows in right, the lower corner temperature of the track corner, the closer measures view to the real view. As the flag shows, the evaluation of the relative pulse error between our measured view and the real view. The data evaluates the transform relate draft between our data and the real track. The low corner temperature of the track corner, the smaller of the errors. As this flag shows, in left flag shows the difference between our system ORB SLAM 2 and the real track. It reflects the system's initially accurate, and the flag in middle shows the deviation of our sketch and the ORB SLAM in X, Y, Z direction compared with the truly track. And the picture in right shows the error between true measures and the real tracks at those tables shows comparisons of the routing derivation and the translation derivation in different systems. It's clear that our solution is more robust and accomplished in dynamic environments than ORB SLAM 2. In this paper, we discussing some SLAM's problems. Firstly, the accurate problems in dynamic environment. Secondly, the limited of the geometric maps. We have posted a solution to solve these problems. We use the semantic segmentation technology of deep learning network to capture moving objects in the margin and using geometric constraints to interrupt the moving object while straight. Or SLAM's gravity in the dynamic environment is improved by moving the future point from moving object. At the same time, we extract semantic information from the segmentation margin and combine it with traditional geometric maps to realize SLAM system's perception of the environment information. After test, our solution has significantly improved, posing a craft and robustness compared to ORB STEM2 in the dynamic environment. However, there are still some problems in our system. For example, static objects in the edge of the margins might be misunderstood as the dynamic object. Because it is disappear from the next frame of the edge, it might not disconnect in the system calculator, which is also the direct of our effect in future. Thank you a lot.
Sleep apnea monitoring system based on channel state information. Sleep apnea is an important factor that affects human health. Traditional approaches based on wearable devices or pressure sensor devices are too expensive to be suitable for daily use, which also don't consider the impact on the breathing frequency when the human body turns over or gets up. In this paper, we propose a system based on Wi-Fi to monitor sleep apnea state. Firstly, we use linear fitting to eliminate the phase errors of the receiving antennas and the wavelet transform to remove the noise of signal amplitude. Secondly, we combine the short-time Fourier transform and the sliding window method to segment the signal. Finally, the features such as the variance of phase difference between antennas are extracted, and the neural network model is built to identify apnea state so as to eliminate interference caused by changes in sleep postures. Experimental results show that the detection accuracy rate for sleep apnea is over 95.6%. Our system can be a daily apnea monitoring approach and provide a health reference for users. Sleep quality is closely related to human health. Some commercial devices collect data from headphones or wristbands worn by users to analyze the quality of sleep. In recent years, because of its non-contact and high privacy characteristics, radar has been widely used in breathing detection. Compared with the radar system, radio frequency identification has the characteristics of simple structure and equipment, and high recognition rate. Therefore, it is also used for vital sign monitoring. With the popularity of Wi-Fi device, Wi-Fi-based respiratory detection technology is gradually becoming a research hotspot. Compared with the superimposed energy information provided by RSSI, channel state information not only carries amplitude information, but also provides phase information of each carrier. In order to simulate the breathing state that may occur during sleep, the human is required to breathe normally in the test area to simulate the breathing state. Stop breathing to simulate apnea. Leave the test area to simulate unmined state. As shown in Figure 1, the sleep state detection proceeds based on Wi-Fi is mainly divided into two stages. In the offline stage, CSI of unmined state, human breathing state, and apnea state are collected respectively. Then we eliminate phase errors and noisy interference in the environment and select the optimal subcarriers. Finally, the feature of the three signs are extracted and a detection classifier is constructed and generated. In the online phase, we collect CSI, proposes signals, and extract signal features in the same way. The classifier built in the offline phase is used to complete the sleep state detection. To characterize the multi-phase propagation, wireless channels are usually modeled with channel impulse response. It can be expressed as Formula 1, where L is a total number of propagation phase. Delta T is the Dirichlet function. Delta L and tau L are the amplitude, attenuation, and time delay of ice pace, respectively. Since multipath transmission shows frequency selective fading in frequency domain, it can be also characterized by channel frequency response HF. CFR and CIR are Fourier transforms, as shown in Formula 2. In the time domain, the accepted signal YT is the convolution of the transmitted signal ST and HT, as shown in Formula 3. Correspondingly, in the frequency domain, the received signal spectrum YF is the product of transmitted signal spectrum SF and HF, as shown in Formula 4. CSI is the sampled version of CFR, assuming that there are k subcarriers on one antenna and m packets are received. The CSI can be expressed as a matrix, as shown in Formula 5. In this paper, the phase error is limited by linear fitting method, and the result compression is shown in Figure 2. It can be seen that the phase after linear calibration is more stable than the original phase, although the proceed phase is not completely equal to the true phase. It is very close to the true value, and the error can be ignored. In the measured environment, due to the multipath effect in the room and the factors of the device, the received signal exhibits various noise, resulting in the required useful signals being submerged in the noise, as shown in the Figure 3. After removing the influence caused by outliers, the wavelet denoising method is used to proceed the CSI amplitude. In this paper, DB3 is used as a wavelet base to decompose the signal in 5 layers. The comparison results before and after denoising are shown as shown in Figure 4. Before denoising, the signal is submerged in noise, and after denoising, the waveform becomes smooth and can reflect the changing state of the channel. Due to the different frequency of the subcarriers, the sensitivity to changes caused by human breathing, apnea, and unmanned state is also different. Therefore, we need to filter out subcarriers that do not change significantly. In this paper, we use the change of CSI amplitude to qualify the sensitivity of subcarriers to sleep state. Assuming that the signal length is m, we calculate the variance of CSI signal of the k subcarriers Vk as shown in Formula 7. This paper uses a sliding window-based method to segment the signal. We assume that the window length is n and the signal length is m, and calculate the variance Vn of the CSI signals difference between two adjacent windows as shown in Formula 8. Then we normalize Vn to get Vn In this paper, we use the difference in phase difference between antennas in the presence of human breathing, apnea, and absence to detect the sleep state of human. we calculate the phase difference d between the antennas and the mean variance range and quarter moment of it, as shown in formula term. For feature extraction, we observed the performance of extracted signal feature through the feature distribution map and randomly take two of features to draw a feature distribution scatter plot as shown in Figure 5. As can be seen in Figure 5a, there is a small amount of confusion between the first feature and the third feature due to the similarity between antenna and unmined state. But from Figure 5b, the first feature and the second feature are almost free of mixed grains and has a clear distribution area, which can better distinguish the three states. The confusion matrix obtained after the classification is shown in Figure 6. Then we calculate its precision and precision recall. Then we use Markov F1 score as a measurement indicator to weight it on average. The calculated macro F1 score is about 0.98. For the accuracy and recall rate in the macro F1 score comprehensive model, the greater the value is, the higher the quality of the classification model is. In this paper, we propose a Wi-Fi-based sleep apnea state detection system that does not require the subject to wear any additional equipment or modify the hardware facilities, which can complete the sleep state only use commercial Wi-Fi equipment. Firstly, we construct the signal model and propose the received signal. Then we design a segmentation algorithm to select the optimal subcarrier and segments the signal. Finally, the feature of segments are extracted and a classifier is constructed to recognize breath, apnea, and unmined state in the sleep state. Experimental results show that this approach can not only eliminate the noise CSI information, but also achieve a recognition accuracy rate of more than 95.6%. How to recognize and detect sleep states for multiple people will become our future work. Thanks for listening.
Hello everyone, I am the second author of this paper, Data Augmentation for Cardiac Magnetic Resonance Imaging, using evolutionary gain. Then I will make a brief statement on the content of this paper from the following aspects. The first part is the research background and introduction of the paper. Cardiac magnetic resonance imaging is known as the gold standard for assessing cardiac function. Conventional cardiac MRI scanning technology has been relatively mature and has played a vital role in disease diagnosis. At present, many cardiac magnetic resonance
image-assisted diagnosis tasks based on deep learning have achieved good results. But cardiac MRI not only require expensive medical equipment to obtain, but also require experienced radiologists to carry out a large number of manual data annotation, which is undoubtedly extremely time-consuming and labor-consuming. In addition, the privacy of patients in the field of medical images has always been very sensitive, so it costs a lot to obtain a large number of data sets that are balanced between positive and negative samples. A great challenge in the field of medical imaging based on deep learning is how to deal with small-scale datasets and the limited number of labeled data. Especially when using complex deep learning model, the dataset is not sufficient or the dataset sample is unbalanced, which will make the deep convolution neural network with huge parameters appear overfitting. In the field of computer vision, scholars have proposed many effective methods for overfitting, such as regularization, dropout, early stopping, weight sharing, weight attenuation, and so on. The above method is to adjust the network structure. In addition, data enhancement is an effective method to operate on the data itself, which alleviates the phenomenon of overfitting in image analysis and classification to a certain extent. Generative adversarial network is a generative model proposed by Ian Goodfellow and others. It consists of generative model G that captures the data distribution and the discriminative model D that estimates the probability that a sample came from the training data rather than G. Finally, the generator obtains the distribution model of real samples and obtains the generation performance close to the real image. The specific structure of GAN is shown below. The entire training process of GAN is to find the balance between the generative network and the discriminative network, which makes the discriminator unable to judge whether the samples generated by the generator are real or generated, so that the generative network can achieve the optimal performance. The main contributions of this paper are as follows. Firstly, a cardiac magnetic resonance medical image data enhancement method based on evolutionary GAN is proposed, which generates high quality and diverse samples to expand the training set, and finally improves the various indicators of the classification results. Secondly, combining the linear interpolation of feature vectors in evolutionary GAN to synthesize new training samples and generate related linear interpolation labels, which not only expands the distribution of the entire training set, but also makes the discrete sample space continuous and improves the smoothness between fields, so that the model can be better trained. The third one is that we use various indicators of downstream classification tasks to optimize the model and the experimental details. The second part is mainly an introduction of evolutionary GAN. The training process of evolutionary GAN can be divided into 3 stages. The first stage is mutation. That is, the parent generator is mutated into multiple offspring generators. The second stage is evaluation. That is, the adaptive score of each offspring generator of the current discriminator is calculated through the fitness function. The third stage is selection. That is, the offspring generator with the highest adaptive score is selected by sorting. The basic structure of the evolutionary GAN is shown below. Evolutionary GAN uses different mutation methods to obtain offspring generators based on parent generators. These mutation operators are actually different training targets. The purpose is to reduce the distance between the generated distribution and the real data distribution through different angles. It should be noted that the best discriminator should be trained before each mutation operation. Evolutionary GAN uses the fitness function to evaluate the generator's performance and quantifies it to the corresponding adaptability score, which can be written as formula. The third part is the research method of this paper. Using GAN for data enhancement requires high quality and diversity of samples. Evolutionary GAN can be stably trained and can generate high quality and diverse samples, so it is very suitable for data enhancement. By adjusting the parameters in the fitness function, you can choose to focus on diversity or quality according to your needs, which can make the data enhancement process more operative. This paper improves the evolutionary GAN and names the improved model Data Augmentation Evolutionary GAN, DAE GAN. The specific network structure is shown below. Although evolutionary GAN greatly improved the diversity of generated samples, a certain number of training samples are required if you want to fully train the GAN model. In the case of too few training samples, the generator and discriminator are prone to reach the equilibrium point prematurely, which will also cause the phenomenon of model collapse in the generated data. In order to alleviate this problem, this paper uses the traditional fine transformation data enhancement method before training GAN, and expands the data through horizontal flip, vertical inversion, translation, rotation, and other operations. Due to the security of medical images, the original data is not added with noise, crop, and other operations, and the texture and the edge features of the original data are retained as far as possible. But traditional data enhancement only makes small changes to the original data and does not generate new features, and the samples are also discrete. Thus, this paper introduces the linear interpolation. Usually, GAN will use the noise Z database, the multivariate uniform distribution or multivariate normal distribution as the input of the model. Matten and others believe that multiple Gaussian distribution can better adapt to the inherent multimodality of the real training data distribution. So a multimodal distribution is used as input in GAN, and it is proved that this method can improve the quality and variety of generated images. The algorithm combined with Gaussian mixture model in this paper is as follows. The first part is the display and the analysis of the experimental results. In order to ensure the consistency of training data, all samples are normalized in this experiment. Before training GAN, the experiment performed the fine transformation data enhancement on the data training set. After the training set is enhanced once, it is divided into two types of operations. One is to put it into the classifier for training directly, and then use the test set to get the classification results. And the other is to put it into different GAN for training. And finally generate new samples to train the classifier again. The original evolutionary GAN uses the structure of DC GAN. In this paper, we consider that the residual network structure can alleviate the gradient vanishing problem and accelerate the convergence speed of the model so as to train the high-performance generator more quickly in the same training time. The ResNet structure are as shown at left is used in the generator and the discriminator in this paper, combined with the self-attention module. The detailed structure of the generator and discriminator and the output size of each layer are shown at right. This experiment uses five-fold cross-validation to dynamically divide the heart magnet resonance image into a training set and a test set at a ratio of 0.8 to 0.2. Training the AE GAN only uses the training set. Due to the uncertainty of deep convolution model in the training process, each model was trained several times, greater than or equal to 5, and the specific effect of data enhancement method was verified by average classification results. Observation method has strong subjectivity. In this experiment, data enhancement is performed on small sample medical images. As a result, the observation method can only be used as a reference evaluation standard. In order to evaluate the effect of data enhancement, this paper uses the ResNet 50 model and the exception model as a classifier. The classification results are used to uniformly evaluate the effects of various data enhancement methods. The fifth part is the summary and the prospect of the paper. Due to limited personal academic level, limited time, and equipment performance, the method proposed in this paper currently has many problems worthy of further improvement and exploration. Firstly, the DAE-GAN model proposed in this paper can effectively expand the amount of cardiac magnetic resonance image data, and effectively alleviate the problem that the classification network cannot be fully trained due to the small amount of medical image data and the uneven data. Secondly, DAE-GAN has a process of survival of the fittest in the training process, compared with ordinary generative or confrontation networks. The training time of this model is relatively long, and the time cost is high. In addition, with the improvement of image resolution, training time will also increase exponentially, and the performance and memory requirements of the graphics card will be higher. The next step of this paper is to further improve training efficiency and reduce time cost while ensuring the synthesis performance of the model. This paper only uses thirdly, this paper only uses the benign and malignant two-category dataset in medical images. For data with more categories, the training efficiency and the synthesis performance can be further improved if it is applied to multi-classification medical image data. It can be considered to integrate label information into conditional generative model. Finally, the references of this paper are listed here. The above is all my explanation of this paper. Thank you for watching.
Hello judges and participants. It's a great honor to be able to participate in this conference and to explain the results of my current research to everyone. The name of my paper is Research on Optimizing the Location and Capacity of Electric Vehicle Charging Stations. And the main research is to comprehensively consider multiple factors in a certain area, and then reasonably deploy charging stations based on these factors. I will explain my paper from these 10 aspects. In this section, I mainly explain the background and the motivation of this paper. This picture shows the number of low-energy vehicles in China from 2040 to the first half of 2020. By observing the pictures, we can find that in the context of environmental protection and resource shortages, the number of electric vehicles and the speed of technological updates are showing a clear upward trend. The official website of the Ministry of Public Security shows that as of June 2020, the number of new energy vehicles in my country is 4.17 million, an increase of 360,000, or 9.145% compared with the end of last year. This section mainly explains the challenges and our solutions. E-waste has become an important part of the new energy development strategy and is the development direction of new energy vehicles. The construction of EV charging stations is a prerequisite for the development and popularization of EVs. Due to the relative high construction cost of charging stations and the large amount of land and power resources they occupy, the development of charging stations is relatively slow. The layout of the charging stations that have been constructed is unreliable in space and has a great blindness. The unreliable deployment of charging stations will affect the urban transportation network planning, increase the driving cost of vehicles, and make it difficult for operators to make a profit or even lose money. Whether the planning of EV charging stations is reasonable will directly affect the number of EVs used and the improvement of service levels. Some literature has important guiding significance for the planning of charging stations, but they ignore that the location of EV charging stations will affect many aspects, which in turn will not be conducive to the development of charging stations, and the different location optimization algorithms. Solving the location problem of the charging station is also a key part. The quality of the selection algorithm is directly related to the accuracy of the final optimization results. Therefore, in the location and capacity model of the charging station, this paper comprehensively considers the actual influencing factors in real life and considers the number of EVs, the charging behavior of users, the cost of building stations and the operation cost of charging stations in different regions, and proposed the location and volume model of EV charging stations on the basis of the traditional particle swarm optimization algorithms is easy to fall into the local optimum. Proposing a differential evolution particle swarm optimization algorithm to verify the feasibility of the model. This section mainly explains the division method of charging demand point. Charging demand is the number of EVs that need to go to the charging station for charging in a certain area and time. The charging demand is closely related to the traffic density. In areas with charging demand, the traffic density near the area will also increase. Therefore, the service capacity of the charging station should match the traffic density of the corresponding area to meet the charging needs of EVs as much as possible. EVs are located in most areas of the city, and vehicles will go to the nearest charging station to charge without the guidance of charging. Therefore, in this paper, the planning area is divided into several small areas, and each small area is a charging demand cell. Some literature proposed that in any area, traffic flow is conserved for a period of time. According to this conclusion, it can be assumed that the number of EVs in each small area remains unchanged. So, for the convenience of calculation, the geometric center of each cell is regarded as a charging node point, according to the number of EVs at each charging node point, calculating the charging demand of each cell. The construction of the charging station not only needs to consider the construction cost of the charging station, but also needs to consider the driving cost of EVs. This paper mainly considers the fixed construction cost of the charging station, the annual operation cost, and the charging satisfaction of EV users, and establishes a mathematical model for the location of EV charging station as shown in EE =1. In equation 1, total cost is the total cost. CSC is the construction cost of the charging station. The construction cost of the charging station is composed of the fixed construction cost and the annual operation cost of the charging station, as shown in equation 2. The fixed construction cost of the charging station is shown in equation 3. By reading a large number of references and completing the simulation environment of this paper, the annual operating cost of the charging station is shown in equal 4. As there is the discounting factor of the charging station as shown in equation 5. EV user satisfaction indicates the evolution of the charging station by the EV users at the charging station as shown in equation 6. In this paper, consider the nominal coefficient of urban roads to calculate the distance traveled by EVs as shown in equation 7. The time-consuming cost of an EV in road is shown in equation 9. And lambda ij is the nominal coefficient of the urban road from the demand point J to the charging station I, as shown in equation 8. The minimum value of nominal ij is 1, and the smaller the nominal ij, the more convenience the traffic between the 2 points. The cost of energy consumption for EV to reach the charging station is shown in equation 11. NC is the number of daily charge of EVs as shown in equation 10. This paper uses the cooling serial multi-server stack modem to establish charging station, the Capacitor allocation modem. In the cooling system of the charging station, the arrival time of EVs follows the negative expansion distribution with the parameter lambda, and the service time of each service desk is independent of each other, with the negative exposure distribution with the parameter mu. The average queue length of the EV at the charging station is shown in equation 12. P is the probability that all charging powers in the charging station are idle, as shown in equation 13. The residence time of EV at a charging station is shown in equation 15. The cost of waiting time of an EV at a charging station is shown in equation 16. The objective function of this paper is shown in equation 17. In equation 17, cost is the lowest cost considering the cost of a charging station and the cost of the EV. This section is the constraint of the modem. The number of charging powers in each charging station is constrained by equation 18. The distance constraint between charging stations is shown in equation 19. The distance constraint from the charging demand point to the charging station is shown in equation 20. In order to avoid the long queue of EVs at a charging station and ensure the stability of the queuing system, the arrival rate of EVs must be less than the product of the service rate of the charging station and the number of charging powers, as shown in equation 21. The residence time limit of EVs at charging stations is shown in equation 22. In this paper, we use the Fourier diagram to divide the service range of the charging station. Fourier diagram is composed of a set of continuous plugins formed by a set of vertical orbitals connecting to adjacent points. In the Fourier diagram, The distance from any point within a polygon to the control point that constitutes the polygon is less than the distance to the control points of other polygons. In this paper, assuming that the coordinates of the charging station are control points, using these control points to draw a Voronoi diagram, the surface area of the charging station can be divided. The first algorithm is improved particle swarm optimization. The improved particle swarm optimization searches the search space in parameters so a group of initialized groups and realize the evolution of the population through the competition and cooperation between individuals in the population. The second algorithm is differential evolution algorithm. Differential evolution algorithm is a group-based adaptive global optimization algorithm. The core part of the algorithm includes mutation, hybridization, and selection operations. In this paper, we added the differential evolution algorithm to the improved particle swarm optimization. The DE algorithm can increase the diversity of the IPSO algorithm population and can better jump out of the local optimism. In other words, this can jump out of the local optimum. This section mainly introduces the simulation parameter of the experiment. The values of these parameters are mainly set with reference to a larger number of Gaussian literatures and the specific environment of experiments. This picture is a location map of charging demand points. In the planning area, there are mainly 34 charging demand cells. Next, we got some results through the above model and environment. This results picture shows the convergence curves of IPSO-D and D-IPSO. In this results picture, we can find that compared with IPSO and DE, DE-IPSO can converge early and can jump out of the local optimum. This result picture shows the changes in the cost of charging stations and the cost of driving EVs with the number of charging stations deployed. In this result picture, we can find that as the charging station increases, the cost of the charging station also increases, because the construction cost of a charging station is positively related to the number of charging stations deployed. The driving cost of EV decreases as the number of charging stations increases. The reason is that as the number of charging stations increases, it will be early for EVs to find the nearest charging station and reduce the distance traveled. This result picture shows the total cost varies with the number of charging stations cost deployed. In this result picture, we can find that when the cost of charging stations and the cost of EVs are considered comprehensively, the total cost of deploying 6 charging stations is the lowest. This is because when the number of charging stations is 6, the total cost of charging station cost and the EVs cost is the lowest. This result table shows the total cost of IPSO, DE, and DE-IPSO changes with the number of charging stations deployed. In this result table, we can find that no matter how many charging stations are deployed, the total cost of using the DE-IPSO algorithm is lower than the IPSO and DE algorithms. This is because the DE algorithm increases the diversity of the IPSO population and reduces the risk of falling into a local optimum. This result picture shows the location distribution of charging stations in the planned area. This result picture shows the service indicators of the charging stations in the charging stations. In this result picture, we can find the average residence time of EVs at a charging station is within 40 minutes. Finally, we make some summary of this paper. This paper comprehensively considering the cost of EV charging and the cost of charging station construction, and proposed a method of location and capacity for EV charging stations. The model of EV charging station location, the model of EV charging station capacity location, and the optimization algorithm of the location of the charging station are studied respectively. The DE-IPSO algorithm is used to verify the feasibility of the site selection model for the site selection of charging stations. The QE0 of this paper can be used to reasonably plan the number of powers in each charging station. By comparing the DE-IPSO and the DE-IPSO algorithms, it's found that the DE-IPSO algorithm can achieve a certain degree jump out of the local optimal solution, finding the global optimal solution, and better deploy the charging station location.
Hello everyone! How do we improve the quality of signal data produced from a given network of heterogeneous sensors without ground truth? I am Ricardo Souza, and together with the co-authors Conceição Amado and Rui Henriques developed AutoMTS, a computational system for the fully autonomous processing of massive time series data. This is the outline of our presentation. We will start with the motivation of this work and we will give the context of it. Most of the domains, like water distribution, traffic monitoring, and physiology systems, have a huge network of heterogeneous sensors. In most cases, these systems have massive georeference time series which are susceptible to failures and errors, mostly because of sensors calibration and problems in the data acquisition, transmission, and storage. These errors could generate duplicates, gross errors, outliers, and missing values. Now we'll speak about the context behind it. This work is under the WISDOM project, which is a partnership between Instituto Superior Técnico and Instituto Politécnico de Setúbal institutes to study sensorized water distribution systems in Portugal. Also, the water utilities Infraquinta, Câmara Municipal de Barreiro, and Câmara Municipal de Beja are also part of this project. The water utilities have multiple heterogeneous sensors spread all over their network, which make these companies able to control and monitor their water distribution systems. Each of the water utilities have unique error profiles and unique regularities, like the water consumption patterns and sampling rate. But what is the main problem? In order to the water utilities have good quality data, it is necessary to process it. But the processing is a laborious task. Why? There are a vast number of state-of-the-art methods available, which have non-trivial selection and parameterization. Each time series have unique regularities and different errors profiles, which lead to different choices of the methods. Also, different sensors have singular calibrations, sampling rates, and positioning within the system. Even more, most of the times, cross-variable relationship in multivariate time series are disregarded. Duplicates is one of the problems that we mentioned before, as you can see in the example what it is. Another problem is the gross errors and the outliers, we consider that the gross error is a value that is impossible to be obtained by a specific sensor. For example, the water pressure can't have negative values. As for the outliers, we consider that they are deviant values from the rest of the data. At last, we consider missing values as observations that should exist in a series but are missing, and can have arbitrarily high duration. Now, we will point out some state-of-the-art methods available along the literature. First, for the outlier detection methods, we can divide into the following categories. Prediction models, where each observation has an outlier score assigned, like it was the deviation from the predict value. Profile-based models, where a profile is created like a baseline from the time series. Each new observation is compared with a profile, and an outlier score is assigned. Information theoretic techniques. If the removal of an observation results in a more succinct representation than the original, the observation is considered an outlier. It is also possible to use classification and clustering techniques in order to detect them. For the missing values, we can divide into three main categories. Single imputation methods, where we can impute the missing values using only one sensor or variable of the data. Multiple imputation methods, where we can input the missing values using multiple sensors or variables of the data. Also, there are other methods to impute the missing values, like ARIMA, TBETS, and the 10-minute flow model from Quevedo. Now about the AutoMTS tool that we developed. The three main contributions of AutoMTS are: give quantities of optimality, where the processing decisions that we make are against ground truth, detect conserved segments, identify the profile of observed errors, and generate artificial errors in the conserved segments for comparison of the processing methods. Also, it covers a large number of methods, some of them with cross-variable dependencies. At last, it is a parameter-free tool which autonomously selects unique parameters. Now we will show about the pipeline of the AutoMTS. Initially is given to the system the time series that you want to process. The first step is the treatment of duplicates, where duplicates are removed from the series. There could be two types of duplicates. First, the duplicates observations have equal values, where simply you can remove either one of them. Second, the duplicates observations have different values. For this type of observations, we turn the observation into a missing value and we try to input the observation with one of our imputation methods. The duplicated value that is closer to the imputed value is the one that stays in our data, and the other is removed. The second step is to detect the typical values, or as I said before, the gross errors. To deal with these values, we just have to use rules. If a value is bigger than x or smaller than y, is turned into a missing observation to be dealt later in the process. The third step is the detection of the outliers. If an outlier is detected, it is given to the user the choice of either remove the outlier from the data, or which is turned into a missing observation, or he can keep the outlier, which can be useful later for monitoring purposes or detect events of interest. These are the methods available for the outlier detection task. All methods are mostly specific for point outliers on the data, for exception of the OutSAX, which mostly works for sequence of outliers. The last step of our pipeline is the imputation of missing values. Here, either the original missing values, the typical values that were turned into missing values, or the outliers that the user chooses to remove are imputed by one of the available methods. These are the methods available for the missing value imputation task. The first three bullets are for univariate methods, and the last two are specific for multivariate. Now we will show some snapshots from the tool and explain how it works. This is the user interface available. We have two main windows where we can change some settings. In the window of the left, we can change the series given by the user. In the window of the right, it is possible to change the pre-processing settings. On the left window, first we have the upload slot, where you can either drag or select from any directory an Excel file. Our tool will check if the file is valid and to be valid it has to follow a specific Excel structure and have at least 4 weeks of data without any missing value. The next slots are used to select and manipulate the series. We can choose the sensor type we want to process, for example, only the water flow sensors. We can also choose by name the specific sensors we want to process. We can select which time period of the series that we want to use. We can select specific days of the calendar, for example, Mondays and weekends. Finally, we can also change the granularity of the series. This last feature can only increase the granularity and never decrease it. On the right window, we can select if you want to impute the missing values and/or detect the outliers. For both of the processing tasks, we can either choose from the following: default, where the method that is selected is a default of the tool; parametric, where the user can select one of the methods available, and if the method is parametric, the user can change the parameters values. At last, the fully automatic option, where our system selects the most promising method available with the best parameters if it is a parametric method. It is also possible to select if you want univariate and/or multivariate methods for the missing values imputation test, or if you want point and/or subsequence methods for the outlier detection test. During the parametric option discussed before, the user can select the method he wants from either of the tests, which will change the parameter settings available right below. We can also change the evaluation settings. The evaluation will be explained later in the presentation. At last, when we have all the settings selected, we just press Run Query for the tool to start working, and will process the series with the option selected. When the tool finishes to run, it will have two visualization panels, one where it will show the series with the missing values imputed, and the other with the detected outliers. It is also possible to download a PDF file with the best methods for each of the selected sensors, with statistical information about the processing. In the end, the user is able to download a new Excel file with the process time series. Now we'll talk about the evaluation used in AutoMTS. The main goal of the evaluation is to select and hyperparameterize the best method for each of the tasks. For that, we can either use the conserved segment of the original time series, which is a sequence of non-polluted observations, or we can generate a synthetic time series using the data distribution of the original time series. Now that we have a non-polluted segment, first we generate artificial outliers and missings used as the faulty data. Here we have 4 different options. We can change a percentage of artificial observations in the data. We can either select if you want points or sequences of observations faulty data observations. We can also select the number of blocks for the sequential observations and the number of sensors affected, or we can choose all or specific ones. Then we run each of the methods and compare their imputed results with the ground truth. In the end, we select the best method for each of the processing tasks. These are the available metrics for each of the tasks, where the F1 score and the root mean squared error are the most important metrics and used mostly as default criteria. But the problem is that for the parametric methods, the parameters that are good for a specific time series could be bad for another. So it is also necessary to find the optimal parameters for each of the parametric methods. For that, we use the Bayesian optimization, which search only the most promising areas of the search space. In this type of search, we want to maximize the F1 score for the outliers and minimize the root mean squared error for the missing values. In this slide, we have 4 examples of the method selection for 2 specific water network sensors, in this case water flow sensor and water pressure sensor, with a different percentage of faulty data for the top 4 methods of each task. It is important to note that the decisions are dependent in the type of sensor. For instance, the interpolation method shows generally the best performance in the water flow sensor, but is not as competitive on the water pressure sensor. In concluding, in order to maintain our evaluation as close as possible to the original data, we use conserved segments of the original series. The method selection process is fully autonomous and parameter-free, which makes it robust against arbitrary type and amount of errors. Although it was designed originally for water distribution systems, it could be used for any kind of domain. Just to finish, here is a 5 illustrative days. This is 5 illustrative days for 2 sensors from 2 different water distribution systems that we used as study case. Our contributions are currently being applied in order to improve the quality of the signals obtained from the sensors placed in the water distribution systems of Portugal. Thank you for your time.
Our paper is Computation Offloading Analyze, based on ready channel in mobile edge computing. Now, I will introduce you some keywords. Gauss channel. Gauss channel, often referred to as weighted wide Gauss noisy channel. It is assumed that the power spectral density is constant over the whole channel bandwidth, and the amplitude conforms to Gauss probability distribution. Ready fitting channel is a statistic modular of radial signal propagation environment. This modular assumes that the amplitude of the signal is random. The SNR in the real environment is shown as formula, where HT is the average transmit power and 0 represents the power spectral density of the noise. B represents the bandwidth of the channel, and AT is the channel power gain with time varying characteristic. Partial compression, offloading, modular. We assume that each raw video can be partitioned into 2 parts, with one compressed locally wide, while the other offloading for head compression. Donate the proportion of the video. K is the compressed portion. And the mobile devices as lambda K belongs to 0 to 1. Then we can introduce the details procedure of partial compression offloading in 3 steps. As mobile device K transmit the remaining bytes to the edge cloud. Then the edge cloud compresses this part of the raw video itself. Finally, the edge cloud combines 2 parts of compressed video and stores into the data store center. Partial offloading theory. The LK means the amount of the data the current user asks to compress, upload, store. Computing resources of the current user, VCK, computing resources allowed by edge cloud-based station. Lambda local computation tasks. Radio. One sub lambda is a mobile edge computing. This picture shows the traditional system in our society. We can see that mobile edge in the future, our mobile devices to the cloud, there have a MEC cloud edge. That means there are more edge cloud computation center in the mobile edge environment. Computation flooding migrates computing tasks to resource-rich devices, which can be located in different locations with the improvement of software requirements for resources. Only in mobile devices and mobile networks cannot be made. Users process requests through the edge server, and the edge server processes the server service nearby, which has real-time performance. For example, in the condition of congested network, any DOS or JIT data can be avoided by reduce the graphics resolution. It is often used in TV news, object recognized, games, and other mobile technologies, but it may need strong computing power to maintain Internet IT services. In our paper, we used simulation method is JX. We assume that the flat fading channel is a RFC-LK, means radio frequency clock. Then, the transmitted signal can be regarded as vertically polarized, and the receiving end and waveform can be regarded as a superposition of a series of plane waves that have undergone M-pass. Then, the specific formula is shown as follows. The random signal RT is used to describe the flat fading signal, which is represented by this character, and CN Rn are independent of each other. Normalize RDT to normalize the power and gate. In our paper, the simulation background is a car received from the signal RFC in different speed. We assume that a mobile terminal at high speed moving communication with the base station. The signal from the base station generates reflected waves due to the band blockage of buildings, bridges, and trees, and any others. Then the signal produced multiple paths fading due to the superposition or attenuation of more multipass effects, the core algorithm we proposed a Part 1 is the frequency distribution map under the RFC and the upper and lower limits of listener. Step 1 initialize frequency, mobile terminal speed, dropper shift. For K is the mod number of signals. Then, the part 2 determine the offloading ratio of computing task under the RFC. Step 1 obtains the transmission rate VSA according to the upper and lower limits of listener. Step 2 build an application offloading transfer module. Step 3 build an application offloading detail delay module based on different VSA according to different division radio lambda to generate the offloading delay variation maximum. That means this algorithm is between different and compare with different channels. The main channels is Rayleigh channel and Gauss channel. So we calculate the average signal X in each channel at the same time and store and calculate the signal power of the noise. Combine signal from n paths, get signal powers. Step 7 calculate the SN under the RFC statistical frequency distribution of SNR. Get the upper limit of SNR by multi-simulation. The compression results are shown in picture 1. The channel capacity data in the experiment are clogged by the Monte Carlo method. We performed 1,000 describe calculations on the static signal-to-noise ratio. The range of a signal is from 20 to 30. Under different values, and then took the average value as the reference. The average SR means is right is big than net. Right picture car speed is 30 kilometers per hour. Left picture car speed is 60 kilometers per hour. The result shows that the smaller the speed of the mobile terminal, the higher the frequency around the average SR. That is, higher the average SR. A large number of simulation results shows that 50% of the signal can achieve a SNR close to 30.42 dB, which is the upper bound SNR of the RFC we simulated, and 85% of the signal can architect SNR close to 20.18 dB. Oh, no, sorry. The red line is Gauss chain. The blue line is Rayleigh chain. Apparently, it means Rayleigh channel have a lower partial upload. In the RFC, under the maximum of the task transmission rate of 30.42 dB, the optimal ratio of the partial offloading is 0.36, and the delay is about 46. In RFC, under the main max of the task transmission rate of 20.18 dB, the optimal ratio of the partial uploading is also 0.40, and the delay is about 63. Conclusion. The simulation result shows that there are errors under the ideal Gauss channel for the proportion of computation tasks offloading, which may upload the computation task more than the actual number of computational tasks can be uploaded. That means, which may cause the following two consequences: increase the probability of congestion, increase the wait delay for uploading computation tasks of local device. In the context of MEC, in order to minimize the delay of the computing task offloading in the terminal mobile device, and to repair the errors in the current mainstream computation offloading strategy, this paper proposes a new evaluation and computation offloading involution method, CLER. The method is based on the RFC. We used the Monte Carlo method to obtain the spectrum of the SNR and obtain the upper and lower limits of the SNR in the RFC through further calculation. And finally, we obtained the optional application of loading retiling. The simulation results are based on the core. The new method will be proposed in this paper, which has a high reference value for the partial offloading of intensive application in MEC environment of the future. It is more accurate and reasonable that emulating the computation of loading retire based on Gauss channel. However, our research also has some shortcomings. On the other hand, For the value of some parameters in the simulation, there are more reasonable and accurate methods in the existing research we need to try. On the other hand, with the simulation range of the computation of loading involution method we proposed, failure is small, so we need to add more simulation environment parameters to increase the generalizability of COER. In short, we still need to do a lot of work to perfect the COER to obtain more and more accurate simulation result. A journey of 1,000 minutes begins with one step. Thank you.